Hello, you're listening to the Eric McKenna Project.
Good. Can you hear me?
I can hear you. You hear me?
Yeah, man.
We're good.
All right, Coop. Appreciate you.
Love being back here, man. Thanks for having me.
It's always good
a
seeing
pleasure.
You across the table.
Hell yeah.
So let's just go. I'll get to obviously what's been on your mind with science. There's some things you're pondering too. But before I forget, because old brain, I will forget. Weird question. So modern technology as we know it, I guess we can go back. Let's go back to the transistor, right?
Okay.
Let's go from there up. That's only 60 years, maybe?
Something like that. Yeah, I'd say maybe like 1930s, 40s. So we're talking, 60, 70 years. Yeah.
Okay, all right. So I'll even give it 70 years. All right. So my question to you is, explain to me how it was possible that the discovery of the subatomic, am I saying that correctly?
Sure, yeah.
How did that actually happen?
Right.
In an era where there was little, if any, quote unquote, technology.
Right, where you couldn't actually see atoms or something like that.
Right. How did the human thought get to the point and get so complex that they could figure out, even we're talking early 1800s was the I always screw the name up. It's not the double slit experiment. Double slit experiment.
Interference experiment.
In regards to whether a photon is a wave or a particle.
Okay,
right?
yeah. So there's a few things.
How did they know?
How did they know? Okay.
They couldn't see it.
Yeah. So first of all, the history of what is called broadly the atomic hypothesis, which is this hypothesis that stuff is made out of these little indivisible units. Because you can't really see these little indivisible units. Like this piece of wood looks like some kind of nice continuous solid.
Okay.
Water looks like some fluid that you could always separate into two smaller pieces of fluid. Then you could separate that into two smaller pieces of fluid. In what sense does water look like it's made out of a bunch of little balls of something, right? So what started the hypothesis, the idea that things were made out of these tiny little atoms? Well, that idea goes way back from well before we had any technology that could possibly justify such an idea. So that idea goes back to this guy named Democritus or Democritus, however you want to pronounce it. And this is we're talking 300, 400 BC, something like that. So this is
BC.
BC. This is ancient Greece. Democritus, he might have been pre-Plato, probably kind of like a contemporary of Socrates, something like that, if I'm getting this right. So he had this idea that's kind of where the idea of an atom came from. And it was not so much...
Where did that idea derive from? Did he explain how he figured that out?
I mean, you'd probably have to ask a classics, like an ancient Greek historian, to try and piece that together. I mean, this is we're getting so far back in time that there isn't a whole lot of just writing in general back then. So I'm not really sure if you could trace the etymology of these ideas super well. A lot of this is based off of writing. This is Aristotle had some writing based off of some stuff from Plato, based off of some conversations he had. You know what I mean? So it's kind of hard to say. But a lot of this atomic hypothesis back then was just to try and explain some qualitative features of things, like that basically the world was made out of different elements, and that these like water and wind and fire and things like that, and that these elements probably had some indivisible unit associated with them, just because the idea of infinity was really something they didn't like, that there must have been something at the end of breaking things in half. Like if you took water and you separated it into two smaller puddles, there had to be an end of that game eventually. You couldn't separate it into smaller puddles forever, right?
Okay.
And then the question was the smallest puddle you could make, right? What would sort of be be the shape of that
core.
right, the core sort of thing. And the idea was that the smallest puddle, or whatever an element, the indivisible atom of water elemental, what that would be, that the shape of that would somehow dictate the properties of water. And so, since water is kind of like slippery, maybe water atoms were sort of round and soft and could slip past each other. And since Earth is kind of rigid, maybe Earth atoms were sort of like blocky, and so they weren't able to sort of like go past each other. And that explained why liquids and solids had like two different properties, because their atoms were two different shapes. And so this atomic hypothesis sort of had explanatory power to sort of explain why you had different phases of matter, like solid, liquid, and gas. Fire maybe like burnt you because it was really sharp and pointy, the little atoms, and so it kind of hurt you whenever it, like, you know what I mean? So like you could maybe come up with some theories that connected these sort of, you know, but they couldn't actually, they didn't have microscopes, they didn't have like anything that could possibly see these.
This is all thought.
This is all just hypothesis, and and of course it wasn't. They would like make up an idea, and then they would go out into the world and say, what would the implications of this idea be? What would that mean for, you know, the way that this stuff would clump together? What would that mean for the way that this would behave when you heat it up, whenever you combine it together? And they would try and like make sense of how their idea would play out in nature. So it was kind of an interesting, you know, game back then, trying to hypothesize this stuff. But of course they couldn't prove any of this stuff. So it was just sort of something that there were people who were atomists that believed in atoms.
Right.
And this continued for basically the next 2,000 years, where there were people who believed in atoms, but there was no real reason one way or the other to not believe or believe. Like they were, right? And that took us all the way into like the 1800s, basically, where there were people that believed in atoms and people that didn't believe in atoms. Prominent physicists who believed in atoms, prominent physicists who didn't believe in atoms. So we really had no idea. Similarly, this brings us to the nature of light. I want to talk about that because you brought this up regarding the double slit experiment. Newton, for example, Isaac Newton, the famous physicist who basically invented physics as we know it today, he was a mathematician slash physicist in the mid 17th century, so 1600s. And
he was the one under the tree in the apple fell, right?
He was the apple tree guy, right? So he was the one that what his sort of, he had a million big contributions, but one of his
Newtonian physics.
One of his main contributions is the idea that gravity that makes apples fall is also the reason why planets orbit each other, right? That the same phenomenon that has to do with apples is the phenomenon that keeps the moon around the Earth, is the phenomenon that keeps the Earth around the sun. Right. So that's Newtonian universal gravitation. So that's why that apple's so famous, because some people might wonder, wait, did Newton invent gravity? Like, people didn't know that stuff fell? No, people didn't know that stuff fell. They didn't know that it was connected to the moon going in circles.
Right on.
Chill. Okay, so Newton thought that light was a little tiny particle, right? And so his sort of idea, he was kind of an atomist when it came to light. He thought light were these little swift moving particles that were moving. Right? And because Newton was such a baller guy who invented calculus and all of mechanics, everyone was just like, if Newton says light's a particle, light's a particle. And there was good reason to believe that. He would draw these diagrams of light going through lenses, of light bouncing off of mirrors, and he would be able to calculate where images were.
Which is still unbelievable in that era of...
Yeah, it was very successful. In no technology, he was able to calculate all sorts of things.
Was there microscopes and things?
Rudimentary. This was right when that was being invented. So the telescope and the microscope were all being invented right around the kind of like late 1500s, early 1600s. Galileo took the sort of like seeing scope that navigators were using on ships in the early 1600s, around 1604, to look up at the stars to see the moons of Jupiter, the phases of Mercury or of Venus. So so this is right around then. This is when, I can never remember his name, it's like Van Leeuwenhoek or whatever, the Dutch guy was using the microscope to see the little microscopic world. So all that stuff was happening right around the 1500s and the 1600s. So but microscopes were not able to see these little particles of light.
Right.
Obviously, microscopes used light to see things, and so you weren't going to be able to use light to see light, in a sense.
Right. Have we ever seen a photon?
what it means to see a photon is a very interesting question, which we could
a visual representation of it.
Yeah,
we'll get there. I didn't mean to take you off course, but that's just fascinating.
In a sense, all you can see are photons all the time. When you're looking at me, all you're seeing are a bunch of photons.
That'll get deep.
Exactly. Okay, so everybody thought light were these little particles, and that got us to this sort of early 1800s experiment around 1802, 1803, whenever this guy named Young, I believe it was Thomas Young, he was this British physicist, did what's called the double slit experiment, where he essentially sent light in through these two tiny little slits, and then that light went into the slits, shone through the two slits, and the two sources of light coming through the slits shone on a screen. And the way that light interfered with each other from those two sources created dark spots and light spots on the screen, right? That's really weird, because if they were particles, like if you just thought of it as like two like hoses that were like spraying particles, then you would expect to see a whole bunch of light behind one slit, a whole bunch of light behind the other slit, and that's it, right? If you sprayed a spray paint can on one and the other, you'd see two splotches of color. But instead what you saw was like light spots, dark spots, light spots, dark spots, light spots, dark spots. And so what that proved is that light was not really a particle, that sometimes it was behaving like what waves do.
Got it.
If you took a water wave and you made water waves and you passed them through two little channels, those water waves would interfere with each other in the exact same way. That high parts of one wave from one little channel would interfere with low parts of another wave from another channel and cancel each other out.
Okay.
So then that's when they thought, okay, maybe light is a wave, but sometimes it behaves like a particle, and then that got into all sorts of confusion. So that's sort of a side narrative to this question of atoms.
Okay.
Where people were still wondering, what about like wood and iron and grass and water? Are those things still atoms? This gets us into the late 1800s.
Okay.
So in the late 1800s, that's whenever we started making real progress on what atoms are. And this brings us to this Austrian mathematical physicist named Ludwig Boltzmann. Have you heard of Boltzmann before?
Yes, I have.
So Boltzmann...
There's a monument to him in his hometown.
There is, indeed. Yeah. So Boltzmann, what his major sort of contribution to physics was to basically take this atomic hypothesis seriously. Say, okay, let's say that the world is made out of tiny little things, and that these tiny little things are constantly just jiggling around, right? That they're basically just knocking into each other, exchanging momentum and energy at all times. And then to basically use the modern, when I say modern, I mean like 1870s, modern tools of calculus and statistics and probability and combinatorics, all the fancy math of his day, to basically figure out statistically what would happen if you had a box of gas. And by gas, I mean like one with 23 zeros after it, particles all bouncing about inside of a box. Or if you had like a solid of little jiggling things that were all oscillating like little springs back and forth, right?
Okay.
And to basically say, like, how would these things expand inside of a box? How would they sort of contract if you crushed the walls of the box in, right? How would they change their kinetic energy as you sort of push the walls in, and these things would bounce off of the walls as the walls compressed and they would speed up, right? How would their average energy change as you crush the walls in? And what he got is he derived all of thermodynamics, which is the sort of study of how, like, heat and, pressure and temperature and volume and how all those things are related to each other, like engines and pistons and energy, all that stuff. He derived all of that from the atomic hypothesis.
Okay.
From just saying, like, thermodynamics is a very old theory that basically explains how, like, if you take a sort of box of gas and you compress it, it'll heat up. If you expand it, it cools, right? That sort of thing. Mm-hmm. The pressure increases if you sort of like compress it. How much does the pressure increase? How much does the temperature increase? That's what we use to make steam engines and things like that, right? But we had no idea really why that was happening. We just knew that, like, okay, there's some theory that explains it. We didn't know what heat was. We actually used to think heat was like a fluid that was maybe flowing into it and flowing out of it whenever things were getting hotter and cooler.
That was a theory.
That was the theory. It was called the calorific theory of heat.
Okay.
Calorific was this like fluid that would flow into things.
Okay.
And it kind of makes sense because when things get hot, they expand. And so the idea was that maybe something was flowing into it and causing it to expand. Heat also flows from hot things to cold things, so it kind of made sense that when you touched a hot thing to a cold thing, something would flow into the cold thing, cause the hot thing to shrink, the cold thing to expand. Like, it kind of makes sense in some sense. And so that was like one of the ideas of what heat was and what was happening. But what Boltzmann realized is like, no, it's because everything is made out of atoms, and that atoms are really just jiggling around. And whenever you put a hot thing next to a cold thing, it's just bumping into it and exchanging energy with it, right? And it's causing the other thing to jiggle around, and that's why the other thing heats up. And I can calculate exactly how much it heats up because it starts to have this little average amount of jiggling energy too, right?
Right.
And because he was able to derive all of these principles of thermodynamics from this one hypothesis, that there exist atoms, that's what convinced the scientific community. Wow, things must be made out of atoms because all this just falls into place. And no one ever saw an atom. We never saw an atom. We just saw the formulas, and we were like, this is a really powerful idea. So I would say by about 1890-ish, 90% of the physics community believed in atoms, and maybe 10% didn't. This is me pulling numbers completely out of my ass, okay? But I'd say most of the physics community, right, believed in atoms after Boltzmann, because this was pretty compelling. This, like, because not only did Boltzmann get on board, but this guy Maxwell, who unified electricity and magnetism. They're called Maxwell's equations, these equations that describe electricity and magnetism. He also, like, teamed up with Boltzmann to do a lot of this work too. And if you got Maxwell on board, then you also, you had some heavy hitters on your team. So people were pretty on board with atoms. How about those last 10%, right? How do we get those last 10% on board? That happened in 1905. Do you know what happened in 1905? Does that year sound familiar? For any physics enthusiasts out there, 1905 should be a famous year. That's not Edwin Hubble's telescope, right? So, that's close, actually. That's around then. That's around that time. I think that was a little bit after. 1905 is... is there a conference or something? So this is called Einstein's miracle year. Have you heard of this before? So Einstein published Brownian Motion, his paper on Brownian Motion, his paper on special relativity, and his paper on the photoelectric effect. In the same year. All in the same year. And this is like, Einstein was born in 1878, so he would have been like, 27 or something when he did all this? So any one of those papers would have made Einstein famous for the rest of his life, and you would have seen him in textbooks. But he did all of these at once, and he wasn't even like a professor. He was like... Not even 30 yet. Yeah. He was 27, and he was working in a patent office, and he was just like doing this in his spare time. Got it. So yeah, this is a pretty impressive feat. But one of these papers in 1905 was on what's called Brownian Motion. It was named after some guy, Brown. Brown's not very famous, but Brownian Motion is famous. And Brownian Motion is the following thing. If you have a little bit of pollen or dust sitting in like a glass of water, and you look at it under a microscope, it goes like this. It spins. It just jiggles. It's just jiggling about. Just jiggle, just bounces about. And people look at it and they're like, what's going on? Is like the table shaking or something? But you keep it really still. You could just like float the table on like a bed of like mercury or something so that it's like completely floating. So there's no oscillations anywhere. And it still is just jiggling about and it's dancing. And so the question is what's causing this? All right. And then after Boltzmann, Einstein was very convinced, right? Einstein was born in 1878-ish. Boltzmann did all this 1870s. So Boltzmann was convinced, well, if atoms exist, then this little piece of dust must be completely berated on all sides by atoms. And so let's calculate statistically what would the little random walk of this dust might be, given the fact that it's being hit on all sides by atoms at all times, right? And so they're measuring the actual movements of it. You can't see the atoms, but you can see the giant thing that's being hit by the atoms, right? And so what he derived was, given the statistical properties of the random walk, given the statistical properties of this thing straying about, what would the size of the atoms be to create that random walk? So
gosh, okay.
you measure the statistical properties of the straying,
Okay.
and from that you can infer the size of the atoms. And so Einstein was able to literally calculate the size of water molecules by measuring the statistics of wandering
their effects
dust
on the
molecules,
dust.
their effects on the
Okay.
dust and on the pollen, which you can see.
Okay.
And so after
It's in
19...
reverse. It's like you
Exactly.
you went backwards to get your hypothesis.
You can infer
Infer.
the size of the atoms
Infer.
from
Okay.
the sort of...
Got it.
So this is where, nowadays we have electron microscopes where you can look at an atom, right?
Right.
But 1905, after that, those last 10% were like, okay, atoms are probably real, right?
Wow. Okay.
So we were very convinced that atoms existed before we ever were able to see any of these. One, because the atomic hypothesis explained thermodynamics once what's called statistical mechanics or Boltzmann's contributions were made. And then two, because Brownian motion, which is the description of how atoms affect the jiggling of little things floating on fluids, was a very robust statistical theory that Einstein derived in 1905. But it's math, basically. With math, we derived atoms. The idea, though, is the same as what Democritus was trying to do thousands of years before, which was you say that atoms exist, you give them certain properties, and then you ask what would those properties imply about the world around us. And you derive the sort of implications of those properties, and you go out and you see if those implications are true. And without ever seeing the atoms, if you see all of the implications of those properties, if you see the result of all of these inferences, then you can infer, right, that these atoms exist. So that's the power of the human mind.
Would that have been the start of the scientific method, or what is the official quote-unquote start of the scientific method?
This is a hot...
Is that different?
This is a
hot topic.
This is the hotly debated thing, and everybody has their like thing that they point.
You mean
like
the origin of the
scientific method?
Okay.
Yeah, I personally have my personal place.
So we're
going to
get your personal.
Coop's take on the start of the
take.
scientific method.
Coop's take.
So where I would place, with all sort of like complex like ideas like the scientific method, it's going to be some sort of emergent contribution that came from an entire like cultural sort of revolution. So you can't, it's kind of a fool's errand to sort of place it at a time in a person or something like that, but it's a fun game to sort of like try and like say, okay, how about this time, this person? So I'm going to do it anyways, but I just want to say that it's the kind of thing that is always sort of like, it's in the air in some sense.
Okay.
And it's not like, like certain scientific discoveries, like general relativity, for example, like a person wrote a paper which like discovered this thing. The pieces that came together to make general relativity, of course, were contributions from other scientists, but the synthesis came from Albert Einstein in 1915.
Got it.
Scientific method is kind of a philosophy that was sort of synthesized by many people over a long time.
All right.
But if I had to like say, okay, here's who I would give it to. Who I would give it to is an Arab philosopher during the golden age of Islam, which was between like 700 and 1250 AD. His name was Al-Hazan, and he was born in Iraq. And so, yeah, like the Greeks did a lot of really awesome stuff, and then that whole region sort of started seeing dark ages after the fall of the Roman Empire, and there was basically not a whole lot going on in Europe between like 200-ish, 200 to 400-ish, all the way up until like 1100.
Okay.
And the question is sort of like, how did that get transferred, right? Between like the ancient Greeks and the sort of scholars of the medieval era leading up to like the Enlightenment and the scientific revolution. And the answer is that ancient Greek traditions and science and knowledge actually got preserved and was being cultivated in the Middle East.
Okay.
In that interim.
Okay.
And in particular, there was a caliphate in the Middle East called the Abbasid Caliphate that was centered in Iraq that was dedicating like something crazy, like 4% of its entire GDP to like translating ancient Greek texts and like developing this sort of like ancient Greek methods. And Alhazen was sort of like a part of this whole thing. So anyways, Alhazen was this philosopher, scientist. He wrote a lot of texts on optics, so a lot of like figuring out like where images are formed from mirrors and lenses and stuff like that. Was like Newton wrote a treatise on optics as well, but a lot of that was based off earlier stuff that was done by people. This is around like 900 1000 AD, something like that. So anyways, why do I give it to him? Because there's a lot of people after him, there's a few people maybe before him, but why I give it to him is because I think there's a few crucial elements to like the scientific method that he is probably the earliest person I could think of that really articulated it well in writing that has survived to this day. So the one thing that is absolutely crucial that he was unequivocal, this is what he stated, was that experiment is like the final say. It is the thing that adjudicates fact. That like
that's proof.
That's proof. That like you can have a theory, it can be beautiful, you can have all sorts of like dogmatic books that suggest that this should be the way that it should be, blah blah blah. Aristotle said this person said this famous. But at the end of the day, if this claim says something about nature and you go out and you do this thing and nature doesn't do it, then it's wrong. And that's all there is to it. And Alhazen was like very much, because this was a very deeply religious society too. And so that was like a big deal to be like, okay, like I am like he was a very deeply religious man too. And he was like, I'm a religious scholar, but at the end of the day, like God made the universe and the universe speaks and we have to listen. And so like, experiment needs to be the final thing that determines what's true and what's not.
So in his day, wouldn't that be like almost heresy?
I mean, it depends on how you phrase it. So they were a little bit more progressive about the way that you sort of interpreted things back then. So like, I mean, I think whether science and religion can be compatible with each other, it's not really one way or the other. I think that and it's clear, I mean, like, there are definitely religious scientists, right? And they find ways to sort of make sense of their cosmology, both from a scientific framework and also from a sort of religious framework. And so I personally am not a religious person, but like but one of my collaborators at NYU, whenever I was at the Center for Cosmology and Particle Physics, he was a very deeply religious person. And I work at Duquesne University, and one of my colleagues on the faculty is a Catholic, practicing Catholic, and he's a physicist at the same time. And so I understand how it's possible for people to create sort of mental rationale for like making sense of how they could separate in their minds like what's going on with like religion, what's going on with their sort of physical description of reality. And it doesn't have to constantly be the way that like, say, during the Spanish Inquisition or like what Galileo had to deal with, like, of course they can come into conflict, but I feel like
they certainly must at certain points, right?
Yeah, there definitely does, and I'm sure there are people during his day that were like Alhazen, like, no, like this is against the Quran, like blah blah blah. They say this in the Quran, but all of these things you're able to create some sort of mental gymnastics to sort of reinterpret and everything like that. I mean, at the end of the day, this is just me sort of shooting from the hip. I'm not very religious, so like I don't know how Alhazen would have said this. This is just me quoting from conversations I've had with my one of my co-authors on some papers I wrote in graduate school. Was a very deeply religious Muslim man, and he was still like he practiced Ramadan very religiously and everything, and he would always say that like he believed that God created the universe, and so anything that the universe did was like God to him, and so like that really justified any kind of practicing of physics. Like if physicists discovered that the Earth went around the sun, that would trump any sort of book that man created that said otherwise, because books are written by men, and the earth is written by God. You know what I mean?
I get it.
And so for him, he was able to sort of square all that.
I get it.
Anyways, Alhazen, he said that basically that experiment is the sort of final thing. That point is the most important thing. The second thing is that, which I think is not really quoted as a part of the scientific method, but I think is really important to the idea of like physics as an enterprise, is Alhazen was one of the main people pushing for the idea that science should be this sort of universal thing. And this is something that I think is a little bit different than a lot of the earlier scientists. Even Aristotle tried to sort of like have a theory for trees and a theory for motion and a theory for this and a theory for that. Alhazen was one of the people that was trying to say, look, if you tell me how rocks roll around on the ground, that should also be how the moon rolls around in the sky. That should be how, tiny little things roll around in the water. That should be how really big things roll around. Like, he had this idea that there should be laws of nature,
like a uniformity,
and that
maybe?
they should be universal laws of nature, right?
Okay.
And that is actually a really big conceptual thing that we kind of take for granted right now.
Right.
And that when somebody questions you on it, you kind of realize you don't really understand why you believe that, but you just do. And I think I might have mentioned this on the show before, this time that I was explaining to my dad one time how variable stars worked.
Yes.
And my dad was like, how do you know that's how they work? And he's like, you've never been there. They're like millions of light years away. And it's like, yeah, I guess I know how they work because all the mechanisms that describe how they work have been tested here on Earth. And I'm making the assumption that the laws of physics on Earth are the same as the laws of physics millions of light years away that we've never been to and we never will go to.
Right.
And so that's sort of an Alhazen thing where it's like there should be these laws that you can just apply to all these different domains and all these different places, and that there is a sort of scientific enterprise that can make sense of like the oneness and totality of the universe.
Okay.
And so that's like another piece, that there are these universal laws that they can be understood through observation. And I feel like there's kind of three things that I really used to pinpoint on him. So universal laws, adjudicated by facts, observation. I think of it, it'll come to me.
That's all right.
Yeah. And another reason why I would really give it to him is because if you look at like who other people will kind of list, they'll list like Galileo or like Roger Bacon or Grosseteste. These are people from like 1500s, 1200s, 1100s in Europe. All of these people in their writing, they cite like who were their teachers. And if you kind of follow this train back of like, okay, well, who were their teachers? Well, who were their teachers? Well, where did they get their ideas from? All of them lead back. They lead back to this guy. I mean, this guy had teachers too, but if you look at his teachers, you see like a break in terms of like the way he was thinking about things.
Okay.
Whereas like if you see the way he was thinking about science, it stays continuous all the way to like this day, right? And so that's why I would kind of say that like,
okay,
I put it on Alhazen, yeah.
You give Alhazen,
yeah,
the creation of the scientific method.
I would say the scientific method started about 1,000 years ago in the Middle East from this guy named Alhazen. Yeah, and then it was propagated into Europe via this Robert Grosseteste guy who was the bishop of the Cathedral of Lincoln, who was a scholar at Oxford when Oxford like was first starting as a university.
Okay.
And he was reading these Middle Eastern scholars, and he is sort of the founder of sort of like European scholasticism, and he passed his stuff to like Roger Bacon and all these people at the University of Paris, and it just sort of like percolated through Europe from there, which eventually led to the scientific revolution with Galileo, which then, everybody from there, yeah.
Okay, right turn.
Got you.
There'll be a couple today.
Yeah, I'm ready for it.
I'm sure you're ready for it. I appreciate that. It kind of ties into what you were talking about just a couple of minutes ago. Are we certain, as we sit here in the year 2021, that it actually is the year 2021? We mentioned just a couple minutes ago, the period of the Dark Ages, where society just couldn't get their shit together, and it was just total freaking chaos. We just somehow believed that the recording of time, however that was done, and we could talk about that because I'm confused on that.
Yeah.
We're actually relying on those that came before us to keep the accurate records, and them that came before them, and those that came before them. How are we sure that we're living in the actual year 2021
That's an
on this
question.
day? And do you have any personal doubts just from you pondering it?
Yeah, that's a good question.
Thank you.
This is we're just shooting from the hip here.
Of course,
I want to
it's
just
Coop's take.
this is Coop's take.
We're going to call these episodes Coop's take.
Coop's take. Coop is not a historian of chronology or anything.
It's science related.
It's science related for sure. What I would say is that I'm fairly confident that we know the year because there are so many different sanity checks if you sort of are going backwards. What I mean by that is there are so many different references of the year that you can keep track of. Like, so many different cultures are keeping track of time, and there are so many touch points of cross connections of we're keeping track in the United Kingdom is keeping very accurate records for a really long time, just because they've been a monarchy for a super long time, and they're constantly interacting with all these other empires which have been around for a very long time. I mean, China's been around for thousands of years, and we can there are scholars who are looking at when these cultures sort of touch each other, and so do those years sort of match up? And then on top of all of these cultural things, of all these different scholars, of all these different empires and things, and when all these different things happen, we also have all these sort of natural things that can kind of make sense of everything.
Okay.
Where this event happened to this empire at this time, and we know the year in which this natural thing happened, and now we can date natural things very precisely.
Okay.
Here's a totally random thing that is mildly related that I just read about the other day, which is super cool. We just recently, for the first time, accurately recorded to the year a date of Europeans being in America before Columbus.
Okay.
We knew that the Norse civilization,
right,
the Vikings were here before,
right,
but we didn't know exactly when. But we have an artifact.
Is it in the Canada region?
In Canada,
okay.
The Newfoundland Labrador sort of island that is off the coast of the kind of Quebec mainland of Canada. It's one of the provinces of Canada. It's in the northeast. It has this little peninsula up there's a settlement up there, an archaeological site, where the Norse people were, and we knew it was a while ago that they were there, but we didn't know exactly when. We found a wooden artifact on this site that was clearly cut with metal. They could tell by the way it was shaved that it was cut by metal, and it was definitely, they didn't have metal, the local people there, so it was clear that. And there was an event in something 960 something,
in the 900s.
In the 900s, when there was a huge amount of there was a solar event where there was a huge amount of cosmic radiation and from the sun. And this radiation from the sun hit the upper atmosphere, and these particles created these cascades of other little particles, whenever high energy particles smashed against the upper atmosphere, they decayed into other little particles, just like in a particle accelerator, when we smash two things together. And that just deposited in all of the life on Earth, this layer of these radioactive isotopes. Very, very faint. It wasn't dangerous to life. It wasn't an extinction event or anything, but you can actually see it with mass spectrometers and things. So we can see in the wood that this thing is made out of, one of the tree rings that is in the wood, the 966, say, or whatever the year was, the like radioactive,
That's incredible.
the radioactive ring that we can see all over the world, so we know that it happened.
Incredible.
And then we can count the rings from 966 to the edge when it was cut, so we know exactly what year it was cut in, and it was 1021. And so we know that and it's 2021. It says 1,000 years ago. So we know that 1,000 years ago, someone cut a wooden thing in Canada and
That's
with
insane.
metal.
That's
so like
insane.
a European. And so there's things like that though that are literally just like littered all over,
Little
the history.
markers.
Little markers here and there that you can constantly just be that you're certain of that are just tied to throughout all of history. And there's historians that are able to sort of tie to these events, to just like, this war happened, this like king died, this trade route thing.
So it's
blah,
based
blah.
about a lot of writings.
So
I would imagine, right?
there's lots of writing, yeah. So, and like I think that I would imagine that like I don't know, just from being, for example, in I went to school for a brief period of time at Oxford, and it sort of expanded my personal like time horizon of like the one of the buildings that was down the street from where I went to class was built in like 1050 something or something like that. And so like thinking of like how do we know it's like 2021, it's like, well, I can get you halfway back, just like this building's been there for like half of that time,
Right.
And so so over that time there's been at least one like continuous civilization that's been around, that's been keeping time. One kind of cool thing is Hallies Comet, which is this comet that is on this pretty long elliptical orbit that we see once every, I think it's 76 years, something like that. We have in the historical record over 2,000 years from some civilization, we have a sighting of this comet, right? And so even that is like a clock where it's like, okay, we have every 76 years, we have some civilization being like, boom, that's that.
But is it accurate down to the second, or is that comet slowing over time? Do we even measure that? I mean,
so
I'm sure somebody's measuring it.
So is the period of this comet slowing? I would say it probably is changing a little bit, but not very much, because it's slowing the same way that probably the Earth a year is changing very, very slightly on Earth, but like
almost
not very
immeasurably.
much. It's very small, yeah.
Okay, talk to me about man and time. So I know even in this century, I think there was an accord between the states for time zones and things. And I think that wasn't it to the point before that? I think trains were running into each other because there was people were kind of just deciding what time it was and just running their life based upon what they thought for their day.
Yeah.
So how did the order of, kind of goofy way to put it, the order of time sounds like something else, but the order of man-made time, how did we all get in synergy with each other, and what was the process of that?
That's a good question. Yeah, I wish I knew more about that, because I think Pittsburgh plays a role in this.
Okay.
So I don't know the details about this, sadly, but what I do know is that the sort of stars used to be. You're right that trains made it important that we actually knew this, that like we kind of roughly had time down where like we knew sort of where the sun was, we knew roughly when noon was, and so it wasn't, you can kind of count from there. And we knew when nighttime was, and so if we were off by a couple minutes or seconds or whatever, it wasn't a big deal. But now when trains had schedules and there were tons of them coming in and out sharing tracks, you had to be accurate down to the second. And so what we started using, where local observatories would actually use positions of celestial objects to be able to keep time down to like the seconds, like where the moon was and the sun and stars, stuff like that.
Sundial, right? Something that's
concept, the idea. The idea of using sort of celestial objects to keep time. But you could do it like very accurately by basically like seeing like, okay, when does like Venus like just come over the horizon or something like that. So the Allegheny Observatory, which is an observatory in the north side here, it was important for determining, I guess it was called like Allegheny Standard Time or something, which eventually became Eastern Standard Time.
Wow.
And so like Eastern Standard Time, which sort of like started this whole like time zone thing, it was kind of based off Allegheny time, which was based off the Allegheny Observatory.
Okay.
So if you take a tour of the Allegheny Observatory on the north side, which is really interesting, there's a ton of like history of the modern world stuff that started in Pittsburgh, our little observatory here, which is kind of cool.
Okay.
But yeah, beyond that little fun factoid, yeah, I really don't know. I mean, it was another thing that's really kind of cool is time was really important for navigation, because if you knew what sort of time zone you were in, because they didn't have time zones back in the day, but if depending on where you were, sort of east-west would depend on when the sun was setting and rising, and that would depend on sort of when noon was, and you could use that to basically know what longitude you were at.
Got it.
And so sailors would use clocks to figure out their position if you had a really accurate clock, because you could like go to an island and you could be like, what time is it here? And I could be like, you're like 7 seconds ahead of me. I must be like this many nautical miles,
Got
like
it.
east
I
or
can
west
see,
of you.
that'd definitely be
right?
important.
And so that's how, yeah. So like people like Christian Huygens, for example, who was a contemporary of Newton, and that's not how you say his name. If there's any Dutch people listening, I know he's a Dutch guy, and so his name is like Huygens or something like that. Anyways, he was a contemporary of Newton, and if it wasn't for Isaac Newton, he would be like a household name, because he was like on track to invent all kinds of stuff with like early mechanics.
Okay.
What we call Newtonian physics might be called Huygens physics, but Newton was just such a badass. Anyways, sorry if we're not allowed to swear on this podcast.
You say anything you want.
Okay, great. Yeah. So anyways, Huygens, one of the things he did that was, very practical and less theoretical, because by the way, physicists, unlike nowadays where physicists just like, make stuff up. Physicists used to do practical things. Like physicists used to like build.
You mean there are a couple out there to do that?
Yeah. Back in the day, physicists used to be like inventors. They used to like be builders. But so one of the things Huygens did is he invented clocks that were like even more accurate than, because pendulums, they're sort of have this property that the period of the pendulum, so how long it takes to go back and forth, is only a function of how long the pendulum is.
Right.
And that is only approximately true. So that's only true if the pendulum isn't disturbed too much, if the amplitude of the pendulum is small.
Okay.
But if the amplitude of the pendulum is small, then it'll sort of wind down because of friction a lot, right? If you want the amplitude to be kind of big so it has enough energy that you don't lose too much friction.
Right.
But if the amplitude's big, then you are outside of the approximation that makes that true, that it doesn't depend, that it only depends on the length. And so what you really need is a sort of pendulum swing that is not a circular swing. You need something that's like kind of a weird, almost parabolic shape. So you need it to kind of change its shape as it goes up and down. Okay. So Huygens invented a sort of clock shape that did that. And the reason why was for navigation. And so, and like that's how these people sort of like justified their existence back then. There weren't sort of like, there wasn't the NSF that would just like give you money to ponder like whether there's 6 dimensions or whatever. You had to actually like invent clocks that would help ships navigate. So time was a really important thing. Like eventually we had to use it so trains didn't collide. But back in the day, it was like, when are you going to plant your crops? Like how are you going to get across the ocean? Like there are all sorts of important.
Where does it get murky? Yeah. Like so I always found this to be fascinating. The concept of BC was or AD was really strange to me because that was actually taking dogma or theology and institutionalizing it into the society, which everybody seems to just use those acronyms like they're nothing. Yeah. And if you go according to the Bible, the King James Bible at least, Jesus was approximately 33-ish years old when whatever happened to him. So before BC was before he was born, and AD was supposed to be after he risen or something. So what happened to 33 years in there? I'm just confused on like,
good question.
What are we using? Like, does AD or BC even mean anything anymore in the conventional thought?
It's just we kind of picked a year and called it 0, and then we went from there. According to the Bible, BC AD transition is supposed to be the year that Jesus was born.
It's okay.
And
I always thought AD was after he had risen. Okay, so there's no gap of 33 odd years.
No, yeah.
Man-made
so there
years
isn't.
in
Yeah,
there.
no, yeah. AD is it's some Latin phrase.
Well, where does it get murky at? Like, because I would think something got murky, because in biblical texts, without getting too deep into that whole realm, they talk about man living hundreds and hundreds of years, and we assume that was because there wasn't a good idea of what time really meant, or I don't know. But aside from biblical issues, where do you think it gets murky in terms of actual human recording, where we're not sure about?
Well, one thing that was really tricky is that we didn't always use this calendar that we use now. What's called, I think it's called the Julian calendar.
Okay.
So the Earth is like a top that is spinning in space, right?
Right.
So you have the Earth, it's sort of spinning like this. But like a top, it is also precessing like this.
Tilt, right?
So the tilt is like this, but the tilt is spinning as well.
On an axis.
So exactly. So not only is it spinning on its axis, but the axis is spinning itself.
So what's that called?
That's called precession. So like when a top is spinning, it's also precessing, right?
Yes.
So why does that matter? Well, why that matters is because when you're sort of tilted away from the sun, it's winter time. When you're tilted towards the sun, it's summertime. But if you're also spinning, then that can also change winter into summer as well.
Okay.
So what that means is that if you're not precessing, then it'll be 6 months and summer will change to winter, vice versa. But if you're also precessing, then after 6 months, right, you'll be a little bit off.
Got it.
And so once we realized that, we were like, oh, we're going to start shifting our seasons by a little bit every single 30 seconds, and then next year will be another 30 seconds, and next year another 30 seconds, and after so many years, fall will turn into winter, which will turn into spring, which will turn into summer, and then July will be spring, and then right, and so we had to adjust the length of the year in order to take that into consideration. So that's why there's one leap year every 4 years, but you don't do a leap year every 20 years or something. You know what I mean?
Got it. See, I didn't get that. Okay.
Yeah. So
it's kind of to catch up, right?
Yeah. So basically, they're
offset that compensate.
You have to compensate for this thing, and we learned that later, and so we had to readjust all the calendars and everything, and different people did it at different times, and so some people still don't do it.
Yes. And today, is it safe to assume that every civilized nation is using standard calendars?
I don't know. It depends. Civilized nation might also be a controversial way to put it too. Yeah.
Oh, very controversial.
yeah. I'm not actually sure. But yeah. So it is definitely. That's one thing that I think gets kind of confusing for historians, is that when they go back, it depends on what calendar you're looking at and when that transition happened. And some people start with 0 as a year. Some people start with 1 as a year.
Oh, I see what you're saying.
And so that kind of shifts everything by 1 year too. So that's kind of confusing.
Well, we do that today. I mean, you sit and think about it. We made a big celebration of, what was it? 9/11, the millennial.
Yeah, the year 2000.
But in reality, what is it? Is it actually the start of 99? It's are we really celebrating the year that we're in?
Yeah.
Or is it really counting it off? Is it really the prior year?
Right. Was 1999 the 2000th year because 0 was a year? Yeah. Were people walking around saying it's year 0? I'm not sure if that was actually happening. Or are they starting with year 1? This is the first year. Probably they started with 1, right? Which means, yeah. So
I don't know.
Yeah. So that's kind of confusing. So the leap day, leap years and leap day.
How modern is that?
That is probably, I don't know actually. That's probably not super modern, because that happens. The leap day thing is not related to the precession. That happens because it's not. And if you think about it, this makes total sense. Why should the number of times the Earth spins be a even multiple of the number of times of how long it takes for the Earth to go around in a circle?
Okay.
Right? And it turns out it's not. It doesn't take exactly 365
Right.
spins to go around in a circle. It's off by about a quarter of a spin, right? Because those motions are totally independent. One is like this, and one is this big long thing.
Right.
So that's what the leap day thing is. The way
Every 4 years.
Every 4 years, and then skipping leap days, like off and on, that compensates for the precession. Where sometimes you skip a leap day, sometimes you don't skip a
I
leap
didn't know
day.
we did that. So
We
every
do
20
that.
years we
Yeah.
skip a leap year.
It's I don't know if it's 20 years or if it's like every 400 years or something. But
okay.
it like I think in the year 2000 we should have had a leap day,
But we didn't. Got
and
it.
that was to sort of do this
Just to
compensation.
set it right.
Yeah, exactly. So we're basically, we kind of like, we make years a little bit longer, some years, some a little bit shorter, to basically dial in the fact that a year is not 365 days, and it's not really 365.25 either, which would be including a fourth of a year.
Right.
It's 365.246253255. And to get that fraction right, you have to add one, then subtract one, then add one every 400 years, then subtract one every 2,000 years, then add one every
Oh
four.
my gosh.
You know what I mean? And so it's like a series that you're adding up that's converging on this number.
So who's the arbiter making sure all that happens when this spans lifetimes? Like, or is it just humans just keeping that emotion, just going forward with it?
It's the Illuminati. Yeah.
Touche.
That's their job. Yeah, that's what they do.
In the year 2021, that's the perfect answer. That's the perfect answer. Okay. I want to talk about what you want to talk about, and we talked a little bit off camera. I want to talk about electric cars.
Oh, okay. Cool.
A little bit.
Yeah.
As well. So, and I'm not trying to put you on the spot. I'm considerably not as wise, but older than my guest here today. So I remember the futility of the 70s in regards to the ecology movement, which started when I was a kid, and the green American flag with the symbol. And I kind of watched like windmill power kind of like raise its head in the 70s and things. But the electric car was kind of almost an impossibility, but it was in the vernacular in the 70s. Can you talk a little bit about why it wasn't possible then, what our limitations were, and how we are now sitting here with Tesla and a couple other companies and even the major manufacturers now entering the system? I drive a Toyota hybrid, and I'm blown away that I can get almost 50 miles to the gallon.
Yeah. It's really
no one talks about how amazing this is. Yet it's been out there for almost 15 years, right?
It's great. Yeah. I mean, I think at the end of the day, there were some innovations with electric motors for sure. I mean, the Tesla motor is a pretty cool piece of engineering. The way that the actual motor itself is able to deliver high torque at low RPMs, meaning that it would deliver a lot of torque when it's going slowly, but it's
like a diesel.
Yeah, but it's also able to deliver a lot of torque when it's going fast too.
Right.
That's where like the Nissan Leaf was kind of like, it was good but that's slow, but then it like wasn't able to go faster than like 80 miles an hour or something.
Right.
The Tesla is able to at like between like 80 miles an hour and 120 miles an hour, it's still able to like accelerate really quickly. So that's a really big innovation. But honestly, the thing that really made all the difference, we could have had Teslas in the 1920s if we just had the batteries. It's really just a battery technology.
Battery technology.
Yeah, I mean, there are pictures of Thomas Edison standing next to an electric car, that they had electric cars in the late 1800s. Like this is not because electric motors were like they were like developed at the same time as internal combustion engines. I mean, the three-phase motor was invented by Tesla. That's why it's called Tesla. The company. And so these things, so this technology is not new, and it's in everything, power tools and everything. And it's been developed for a long time. Golf carts. They're gigantic industrial electric motors, so they're very capable of moving large equipment for sure. It was just that you need an enormous amount of energy in order to move a gigantic steel box. And it's just really, really hard to beat the energy density of gasoline. So gasoline per kilogram just has so much energy. So if you have to carry your energy with you, which if you're moving in a mobile thing like a car, you can't carry the plug with you. That's the extension cord, right? You have to actually like have it in your trunk or whatever, like in a tank. If you have to take your energy with you, then you don't want it to weigh very much, or else you're going to need more energy to compensate for that weight. Right. And so we just needed to invent a technology that had an energy density, right? So energy per volume that was high, that was at a cost that was competitive.
Got it.
And it took the sort of digital revolution, like laptops and cell phones, before there was an industrial scale economic push to create batteries that were sort of cost and size competitive enough to do that, right? That like without like this massive push in the lithium ion technology sphere, which came from like phones and laptops,
goes back
and things
like
like
to the
that.
early 90s with
Exactly,
the
like camcorders and all that sort of thing. Like once that stuff started being developed, that's when all of a sudden it was like, okay, this is a technology that has the energy density. And by the way, it's still like a Model 3 Tesla weighs as much as my pickup truck. It's a very heavy car, and it's pretty much all battery. Like the battery is still very heavy compared to a gas tank. It's extremely heavy, so it's still not as energy dense as gasoline, but it is just enough that like you can put it in a car and you can make this thing go. So it is battery technology.
So that's our limitation is the delivery.
It is the energy. And then.
So is that not to go down the economics thing, but is that essentially what the worth of the Tesla Corporation is their battery technology, or is it really the car?
There's a few things I would say that really make Tesla, like why their market cap is insane. Part of it is a lot of hype, for sure.
Oh,
and like Elon Musk and all that. Like, let's not even get into it. But yeah, so why? So one thing, so their battery technology is really good. They're doing this sort of like Rockefeller, Carnegie vertical integration thing, where they're not just like making a car; they're trying to do like everything,
roofing tiles and
so like
Hyperloop
energy
or whatever
production.
it is.
Yeah, so not just diversifying. What I mean by vertical integration, is they want to make the batteries which go into the car, and they want to be the person who sells the car. Like they want to do everything.
The whole chain.
Yeah, they want to do the whole chain from like the raw materials all the way up.
Like how they build a Lamborghini, or they used to, anyways. They make the nuts that go in, the bolts that go in the car.
There you go. Yeah. So instead of like buying, and of course like the batteries, they have partnerships with Panasonic and LG and stuff like that. But they also are developing battery technology and battery factories and everything. So one thing is that they are being very innovative in that like they're developing their own technology to go into the car. Their software development thing is like way ahead of everybody in terms of like the AI side of Tesla for self-driving capabilities, things like that. Their whole framework is a little different, where they sort of see a car more as a piece of technology, I think, than like a machine. Like their sort of perspective of a car is like, you have like this iPad that's like sitting there that you're sort of interacting with to like manipulate the car, as opposed to this sort of like knobs and stuff like that. And like you get like software updates for your car all the time, and you sort of like can activate features of your car by paying for them, and you can get like you can get like monthly subscriptions to various aspects of the car. So their entire sort of model of their entire business model is a little bit more sort of like thinking in this sort of 21st century way of how we interact with things. And I think that like
it's how they view the car as a product which is different.
And I think investors kind of see that, and they kind of see that as the future, and they see Tesla kind of being ahead of the game that way. And I think they do see that Tesla is becoming this like distributed energy company, where it's like they're going to develop the roof tiles, the power walls in the car, and the roof is going to charge up the power wall, which is going to charge up your car. And you don't need a generator, because your car can actually charge your house if your power goes down, because your car has an 85 kilowatt hour battery. And then once your sort of the sun comes out, then your roof is going to recharge your car that was charging your house.
It all makes sense.
And then once you have extra battery, then that can go into the grid, and you can make money off that. And when you're not using your car, your self-driving car can go pick people up as a robo-taxi, and you can make money off of that. And so like they're just sort of like thinking of Tesla as this sort of like giant like integrated thing that is not just sort of like it's a van that you pick your kids up from soccer with, you know what I mean? Like it's a new kind of like whole product suite that I think is kind of interesting. So
Huh.
Yeah.
Now, there's competition. I think there's a company called Lucid. I've been paying attention. There's other people coming naturally.
Oh, yeah.
Naturally.
Yeah. The Rivian is making a pretty cool electric truck, which is pretty sweet.
Yes, I saw that.
GM,
Is that out yet?
The Rivian truck, I think, is taking orders now.
Okay.
It's
pricey.
I don't know if you can. Oh, yeah. Yeah. But it went down. It was originally 75, and I think now it's like 62.
Oh, really?
Or
I thought it was over 100. Okay.
You can get feature packages that put it over 100, but its base model is in the 60s, which is pretty good. Yeah. So, but when we got the electrifying transport is a really big part of bringing emissions down, because for the U.S., I'm pretty sure the largest emission sector is cars.
I would think.
And so that's a really big thing for us to do that. Now, where that electricity comes from is also really important. So if we have coal power plants and we're charging cars with coal power plants, then that
defeats the purpose.
Kind of. What I want to point out, though, which I think a lot of people that criticize electric vehicles say, oh, who cares? Like, if we charge them with natural gas and coal, then it's the same. It's still not the same. That electric cars are still, even if you charge them with coal power plants, they're still better. And the reason is because electric motors are way, way, way more efficient than internal combustion engines. Internal combustion...
So use less electricity.
Yeah, they use less energy generally.
Energy in general, right.
That creating movement by exploding gasoline inside of a chamber to expand a piston.
It's kind of horrifying when you think about it like that.
It is a bit terrifying. You're sitting in front of a controlled explosion in front of you. That an internal combustion engine its theoretical optimal efficiency is only like 30 or 40% or something like that, right? Whereas like a coal-fired power plant, its efficiency is higher than that. So it's more efficient that way. Also, with electric vehicles, you have regenerative braking, which can get you back a ton of the energy.
I think that's what I just learned this, but that's how the battery mainly gets charged in my hybrid.
Your hybrid has regenerative braking, which is huge. Yeah, I have an e-bike and it has regenerative braking too, which keeps my battery really well charged up. So
I see like this diagram, it shows the transfer of energy between the combustion engines to the battery, and it changes, and I just stare at that. I have no idea what I'm looking at.
Yeah.
I didn't even know that it was the braking that was charging my battery. I thought it was combination of the alternator doing that through the combustion engine running. I'm so confused.
Yeah, there's two ways. I mean, there's the drive shaft turning the brush in the alternator, which is generating electricity, charging the battery. But there's also the brakes. I mean, if you think about, so just like an order of magnitude, this is going to get a little mathy, and so if you're afraid of math, feel free to grab a coffee or something. So the energy that like my truck has on the highway. So let's say that like I have to come to a complete stop on the highway. Okay, so on the highway, let's make the numbers easy for my brain. Let's say I'm going like 100 miles an hour. So in
he does do that,
right? Yeah, it's possible. I try not to. In physics numbers, that's 50 meters per second.
Okay.
And let's say that the mass of my truck is something like 2,000 kilograms, something like that. Okay. So the kinetic energy of my truck is 1/2 times the mass of my truck times the speed squared. So 1/2 times 2,000 kilograms times 50 meters per second squared. Okay. So 1/2 of 2,000 is 1,000.
Yes.
50 squared is 2,500. Right.
Okay.
So 1,000, 2,500. So that's 2.5 million joules of energy. Right. So 2.5 megajoules. 2.5 megajoules. Gasoline per kilogram is about 10 megajoules of energy. So that means that every time I stop on the highway, that is 250 grams of gasoline worth of energy. How much is 250 grams of gasoline? Well, a pound is 500 grams of gasoline, right? So that's half a pound, which is a 1/16 of a gallon.
Wow.
Right? So every time I brake, that's like a 1/16 of a gallon that I could get back if I had regenerative brakes, right? So braking 16 times is a gallon of gas, right? So that's a ton of energy that you lose. And where does that energy go? Your brake pads just make your wheel wells really hot, right? That's
exactly
all that energy just turns into heat.
Exactly right.
So that's an enormous amount of wasted energy. And so just from regenerative braking and the lack of internal combustion engine, electric cars would be better even if we didn't switch any of our electricity grid. But now that we have electric cars, now we can electrify the grid, and then you have no emissions at all. And so that's obviously ideal.
So it comes down to battery technology then.
But battery technology is the big breakthrough. That's what makes it huge. And we still need to do better because batteries are super heavy and they're still pretty expensive.
You think that's the next big technology breakthrough? My buddy of mine said about 10 years ago, we were sitting around one day pondering. We're two non-scientific people just pondering, like, what is the next thing? Because we looked at our life, Coop, and we have everything. Like, you're holding a phone. I mean, you can't get the phone much smaller and make it functional. There's a limitation based upon our physics, how we're made. It's a human. We have watches. I mean, it's things are being reduced, being made faster, smaller, more convenient, but there's a limitation in terms of functionality. What's the next thing? And the only thing we could possibly come up with, and this was like 10 years ago, was that, I don't know, battery, portable energy. That's one area we could get better at. Yeah. Maybe?
Yeah, I think that's a big thing. I mean, I think definitely energy storage is really important for renewable energy because it's not on all the time, the way that like you can just throw coal into a fire, you can just throw oil into a fire. Like wind blows sometimes, it doesn't some other times, right? The sun shines sometimes. So you need to, if you're generating extra energy, you need to save it for when the wind isn't blowing. And so you need to be able to store that excess energy. And so that's one thing that we need to innovate on. Lithium ion is good.
Talk about that. That's an element, right? Lithium is an element?
Yeah, so lithium is an element. Yeah, so let's talk about what's going on there. So everything that's in your phone, in your computer, these things basically use this one kind of element called lithium. And lithium is one of the lightest elements in the universe. If you look at the periodic table, the smallest one is hydrogen.
Right.
1 in the periodic table. 2 is helium. 3
He, by the way.
He, yeah, for those who listen, right? +1 air. 3 is lithium. Right, so lithium is 3 in the periodic table. Yeah.
Is that Li?
Li. Yeah.
All right.
So basically, and it's good that it's so light. That's why we're able to have such a high energy density because it's such a small, light element. We're able to have so many of these lithium ions crammed together in such a small amount of space.
Got it.
But because of that energy density, it's like explosive. Like if you took a lithium ion battery and hit it with a hammer, it would explode. So that's the element that we need to mine and harvest in order to make these batteries. And it's not trivial to mine this thing, by the way. Most of the lithium is found in this little thing called the lithium triangle in South America, in like Argentina, Chile, and Bolivia.
I probably say it's a pretty valuable area now.
It's a very valuable area now, and it's like completely disrupting the politics in that area. It's getting pretty crazy there. Yeah, it's also, there's some in Australia as well. We have some lithium actually in the Southwest as well. So there's a lot of lithium deposits that are undeveloped.
Is it true that there's a lot of it on the moon? That's something I read too.
Yeah, there's a lot of it everywhere. It's the third most abundant element in the universe.
Okay.
So it's just a kind of matter of getting it. And the way that we kind of harvest it is you basically grind up a whole bunch of rocks and then dissolve a lot of it into water, and then you spread the water into these pools and you let the sun evaporate the water out, and then the crystal stuff that's left over from this brine is this salt, and the salt, a huge component of that salt is lithium. So you basically need a ton of water.
Wow.
And you make these huge brine pools and you evaporate it. It's the same way that the Romans actually mined salt, like table salt.
Wow.
Is the way that we're mining like lithium. So anyways, it takes a lot of space, it takes a lot of water. So even though we have millions of tons of it on reserve, Chile, which has like the most lithium, only mined like 10,000 or 15,000 tons or something last year. So anyways, lithium is what a lot of these batteries are made out of, but for grid storage, like storage for the electrical grid, it's probably not the best solution.
Okay.
So they're coming up with a lot of really cool solutions right now.
Just talk about them.
So one of the things that they're doing, which I think is one of the slickest things, is they have these gigantic containers full of really dense rocks. So you have one giant container full of rock called basalt, which is like what the ocean floor is made out of, and then another really dense container of rocks. And what you do is you use excess electricity to basically heat up one container of rock to like hundreds of degrees Celsius. And you insulate it super well. So it's just like a giant heat battery. And this container, you keep cool to like maybe like negative 10 degrees.
Okay.
And you have a pipe that is connecting this thing. And whenever you want energy, you just open a valve. And from the gas that's super heated inside of here, expanding into the colder container of rocks, that gas will just go through this expander that will turn a turbine, and it'll just generate tons and tons of electricity, and it'll heat up all of these rocks inside of here. And then you could have another tube on the bottom that's creating like a pressure differential so that all of the gas sort of moves from one side to the other one, and then you can get all of this like hundreds of degrees of energy back.
Okay.
And then it goes to equilibrium, and then you can charge it back up by basically just heating one side back up again.
Okay, but how do you heat that one side?
You heat it up by basically using excess energy from solar or wind. So basically, whenever the sun is shining and you have more energy than you need, you take that extra energy to heat up all these rocks. And then whenever the sun goes down and you have peak demand because everyone's coming home from work, you just release all of those hot rocks.
Okay.
And it actually, they're getting round trip efficiency, meaning that like they get what percentage of the energy do they get back from releasing all of the hot rocks? They're getting round trip efficiencies of like 70% or something like that. So basically, if you put 1 million units of energy in, you get like 700,000 units of energy back, which is pretty good. And it's cheap. It's a pile of rocks, right?
Yeah.
And so you don't need some crazy lithium ion, but basalt is what most of the ocean floor is made out of.
So what are unique about the properties of basalt that does that?
It has a high heat capacity, meaning that a certain amount of energy creates a certain amount of temperature change. And so high heat capacity means that a large amount of energy creates a small amount of temperature change.
Okay.
And so if you wanted to store a huge amount of energy in it without heating it up too much, then you want it to have a high heat capacity.
Got it.
What's an example of something with a high heat capacity? Water, right? That's why we're made out of water, because we don't want to go outside whenever it's 20 degrees and freeze to death. Why don't we freeze to death? We're 98.6 degrees and it's 20 degrees outside. Why don't we just die when we go outside? Because water has a high heat capacity, so it takes an enormous amount of energy transfer for us to change our temperature.
Got it.
Right? It takes a lot of energy to boil water on the stove. We have to light a flame underneath it and wait like 20 minutes for that water to boil. Why? Because water has a high heat capacity. It takes an enormous amount of energy to change the temperature of water.
Got it.
So that's why we use basalt. So that's like a cheaper way. You can't really do that in a Tesla, unfortunately, but you could do that for like grid storage, for example.
What other kind of technology are you looking at? Do you know?
Yeah. So here's something that I'd love to just throw a pitch out there to keep on people's radar. So this isn't a piece of technology. This is a science experiment that is going that I just want to get everyone stoked about.
All right.
The James Webb Space Telescope.
Yes.
Which I believe I might have mentioned on the show in the past because it's been in development for a good 25 years now.
Right.
It is going to fly, hopefully, finally, on, I believe, December 18th.
You mean like 2 months from now?
Yeah.
Finally.
Yeah, finally.
Okay.
Last time I was on the show, I might have said the James Webb Space Telescope is flying on Halloween of 2021, right?
I think you did. I think you did.
Yeah. But that's the new date, and it is already at the launch pad, and so I think it is going to actually happen this time.
What is so special about this?
Okay, so this is the update of Hubble, right? So the Hubble Space Telescope, right? This thing started its planning in the 1970s, launched in like the 1990s, and it was our premier space telescope.
Yes.
And the Hubble was cool, but it was about 2.5 meters diameter telescope. In terms of its mirror, which is pretty good. It's like a 10-foot mirror. But James Webb Space Telescope is going to be basically a flying observatory. It's going to have a 6.5 meter diameter telescope. So for people who aren't really familiar with meters, a meter is like a yard, basically.
Right.
So 6.5 yards is like 20-some feet, right? So an absolutely enormous telescope. And this thing is going to be what's called an infrared telescope.
Okay.
So it sees a kind of light that is not the sort of visible light that you and I see. It sees light that is emitted by things that are very cool. Okay. So like, light bulbs are very hot, which is why we see them, right? But things that are very cool emit infrared light. So, for example, night vision goggles see infrared. Why do they see infrared? Because when it's dark, you and I are emitting infrared light.
Right.
Our bodies are hot enough to emit infrared light. If it's looking at stars, which are very hot, why would you want to see infrared light? The reason is because the James Webb Space Telescope is going to be looking for stars that are so far away that the expansion of the universe will have stretched the light out so much that it will take what used to be visible light and will stretch that light into infrared light.
Okay.
So the James Webb Space Telescope is going to look at light that is basically as old as we could possibly see. There is a limit to how far back in the past we can see. At some point in the past, the universe was not see-through. At some point in the past, the universe was a hot ball of plasma.
Right.
And you can't see through a hot ball of plasma.
Right.
So there's like a...
Do they estimate when that was in terms of what time that was?
Yeah, that was about 14.5 billion years ago. So we're going to be looking at stuff that was like 14 billion years old.
But I mean, from the time of the Big Bang to the point where we can't see past,
yeah,
is there a time? What's the time in between that?
I think it's like 300,000 years or something like that. Yeah.
Okay.
So there's a few 100,000 years where
just a few 100,000 years.
Yeah, just a couple 100,000 years where it's just plasma.
Okay.
And
so we can't see the Big Bang. We can't.
No.
We don't have the technology to see it. The actual.
Right.
Singularity.
The singularity, yeah. So presumably there was no singularity. Our theories, general relativity says there was a singularity, but we know general relativity at some point is wrong.
Okay.
Because we know quantum mechanics has to be involved, and general relativity doesn't include quantum mechanics.
Right.
But no, we can't see past this surface in time where the universe becomes a hot ball of plasma. This surface in time, by the way, is called the cosmic microwave background. Right? We've seen.
That was my question too, because we have a photo of that Hubble took that photo, right?
Yeah.
So what is Webb going to do that is going to be more accurate than that?
So what Webb is going to do is it's going to, so we can see like photons from that surface coming in all directions. But what we haven't seen are galaxies that are like right in front of that surface, basically, in space.
Okay.
Because those galaxies are so redshifted from being so far away, which means their light is so stretched out that the light can't be seen by Hubble. Why can't Hubble see it? Hubble is right next to the Earth, basically. And the Earth is like a giant glowing light bulb in the infrared. So if you want to see something that is stretched out like that, you need to be really far away from the Earth.
I get it.
Right? So the James Webb Space Telescope, we're launching, and we're going to place it at this very special point that's called the L2 Lagrange point.
Okay.
Right? So you have the Earth, and you have this...
Somehow I think ZZ Top's out there.
He probably is just floating around. You have the sun and you have the Earth, and there's a point that is in line with both the sun and the Earth. It's like all the way over here.
Okay.
And if you place something over here, exactly at this point that is in line with the sun and the Earth, and you have it rotate right there, it'll stay exactly right there. Okay? So why would you want to do that? You want to do that because if you put a shield on this side of your spacecraft, it'll always block both the Earth and the sun.
Got it. Okay.
So that's what we're doing, is we're making an observatory. We're putting it at the L2 Lagrange point. We're putting a shield on this side so that it blocks the Earth here and the sun here, and it's just going to have a giant telescope like this, and it's going to look at the sky like that.
Got it.
Right? So this thing has this giant 6.5 meter telescope. It's so big it doesn't fit inside of a rocket. So it can't be one giant mirror. It's made out of these hexagons, these beryllium gold-plated hexagons that all have to fold up so that way it can sort of fold into this configuration. And it has to fold into this rocket. And then automatically, when it gets to the Lagrange point, it has to deploy itself. It has to unfold this hexagonal mirror, and then its sun shield has to sort of, like origami, it has to unfold, right? And so you get this giant, like almost like football field sized thing.
That's insane.
And all of this has to weigh like 10,000 kilograms or something because it has to be launched in a rocket. So yeah.
And how long has this been in development?
So this is a bit of a touchy topic for NASA. So this thing started development in 1996, when I was 9 years old.
Okay.
And it was projected to launch in 2007.
Okay.
And it was supposed to cost $500 million. So, for those of you keeping score at home, it is not 2007. In case you're watching this podcast a long time in the future, it is not 2007 this year. It is 2021. So we're a little behind schedule, about 14 years behind schedule.
What has been the delay, as far as you know?
So part of the delay is that, like, technology has changed so rapidly over the last 20 years that we wanted to add stuff. Like, as new stuff came on, we were like, oh, this is expensive. We're only going to get one shot at this. Like, let's add this to it. Let's add this to it. Part of it has been, this is a lot harder doing this crazy once, like, we're inventing all this technology as we're going. These crazy beryllium hexagon folded mirror things are taking long. Part of it is that it's so expensive that we want to make sure that it doesn't fail. And so, like, one of the tests you have to do is you basically put the entire instrument on a giant shake table. Like, by a giant shake table, I mean like a warehouse-sized shake table, and you simulate what it feels like to be inside of a rocket ship. And if anything shakes loose, you have to, like, basically start from scratch and be like, what happened? Where did that piece come from? Why did it shake loose? And so there are many times where it was like they would shake it and they would find one screw on the ground and be like, take it apart. Because that screw could be in the thing that holds one side of the sun shield, and if that comes apart, the thing needs to stay below 50 degrees Kelvin in order to be able to see things.
Got it.
And so what it should have been $500 million, instead it's about $10 billion. So it's a factor of 20 cost overrun, and it's,
just hope it doesn't blow up on launch.
That's the thing, yeah. So the European Space Agency is in charge of the launch. So NASA made the thing. Let's hope the Europeans get the launch right. Yeah. So yeah, it's in French Guiana right now. So France, part of France is, France still has one of its colonies. Part of France is in South America.
Right.
And so they have a launch port in South America, very close to the equator.
Okay.
Which is where you want to launch rockets, because the Earth is spinning. And if you look at the size of the Earth, it's pretty big to make a full rotation in 24 hours. So if you're on the equator of the Earth, you're going really fast. Your tangential speed is really fast.
Right.
So if you launch a rocket from the equator, then you don't need nearly as much fuel to get off the Earth. And that's why our launch pads are in Florida. The Soviets are like down south in like Kazakhstan or whatever.
Oh, I didn't know that.
Yeah, that's why we do everything as far south as possible. The French happen to have a colony in South America, and so that's why the launch pad is in French Guiana.
Okay, so from the time it launches to the time it gets in place and starts sending data back, what are we looking at?
Oh, good question. Yeah, I mean, it'll take a while to get out there. It's out past the moon, so it'll take, probably a few days just to get there, and then it'll have to unfold, and then, I don't know. I would guess probably in the summer, maybe.
So there's nothing out there that's around it that can take a picture and watching it unfold, right? We can't actually watch
Good question.
It unfold.
That'd be really cool. No, I don't think
amazing.
So. That would be really sweet. Yeah. No, yeah.
I don't spend $10 billion. What's another $1 billion to throw a little satellite up running beside it just to take pictures, right?
We're sending William Shatner up there. Like, why can't Bezos just do that? Yeah, seriously. Yeah, that'd be really cool. But anyways, yeah. So that's a really exciting piece of technology that I'm pretty stoked about. Here's one that I think, going back to the green energy thing that I wanted to bring up, which I saw recently that I was pretty excited about. And this is because I wanted to bring this up because, we're in Appalachia here, right? And we basically invented the fossil fuel economy, right? Like oil, the first commercial oil refinery was here in Western Pennsylvania.
Right.
And so, there's a lot of people and probably a lot of listeners who kind of depend on the oil economy. My father worked in natural gas up until he retired like a couple of years ago. And something that I thought was really kind of promising was these folks came up with this really cool project. It's very similar to the hot rocks thing. Okay. It's basically this insulated box. It's like the size of like a cargo container, and you fill it with this metal that you can, again, with excess energy, you can melt and you can make molten metal into it, and you can use it as essentially a thermal battery, the same way the rocks were storing energy with heat.
All right.
You can use molten metal to store the energy that way too. Why do I bring this up here? Because the way they designed it is you can basically take a coal power plant and you could take the burners that burn coal, basically the boiler system that you use to just take a coal oven and you burn the coal to boil the water, and then that generates electricity, or a natural gas power plant where you burn the natural gas to boil water to turn a turbine, and you could just remove that bit and you could put one of these thermal batteries in instead, and you can reuse all of the infrastructure for the coal power plant.
Amazing.
You can reuse all of the infrastructure for the natural gas power plant, and instead of using coal and natural gas as your energy source, you use excess energy from windmills in Somerset, excess energy from solar farms all over the Appalachian countryside. So basically, we would build up all of our renewable infrastructure here in Appalachia. We would all the excess electricity send to all these old power plants. All these people would kind of keep their jobs, create some new jobs, and we'd have all of this old infrastructure, and they'd still be power plants. They just, instead of burning things, they would boil water to generate electricity using the thermal batteries that were being charged by renewables, as opposed to using fossil fuels. So I thought that was kind of sweet too.
So where are they at now? Just the idea? Is they still in the idea phase?
They are deploying one of these in Europe at the moment. So they already made a demonstration one to show that it works, and they're deploying one commercially in Europe. I forget where. It's in Eastern Europe somewhere. But yeah, it's a thing that exists, and they're actually deploying it right now. So we'll see how well it performs in terms of its round trip efficiency, in terms of life cycles. I mean, one of the things that's hard about these thermal battery things is that in order for them to be efficient, they have to be really hot, and they have to maintain that temperature over many life cycles. And the biggest challenge is just that, how do you keep your equipment from getting damaged whenever it's right next to something that's 1,000 degrees or something like that, right?
Got it.
And so the conceptually, it's all very simple. It's just in practice, engineering wise, if this is supposed to be a solution to the power grid that's supposed to last 50 years or whatever, how's it going to actually play out? And so I think it'll be really good to see this thing in the wild, to see how it does. But this is something that I'm pretty excited about, just because I think that any sort of transition away from fossil fuels, in order for it to work, it just needs to include, the old fossil fuel economy in order to get people on board. I mean, we're seeing that.
Well, that'd be an amazing synergy if that could happen.
It would be, yeah, because we're seeing that right now, where Joe Manchin is not supporting any of this legislation. And why? Because he's a West Virginia senator, and West Virginia is depending on a lot of this stuff. And I think that one way to sort of come up with a compromise is well, how do you include these people in the new economy? And this is an interesting solution.
Which should be their job. I mean, you think the job of our legislatures anyways.
Exactly. Yeah. If you're in charge of representing these people, then try and come up with some solutions that help them. Yeah.
Okay, couple random questions for you. We're sending you all over the place today.
All right.
Do you believe that we have, in the year 2021, we have the scientific ability to have a telescope powerful enough to look at the footprint on the moon from the moon landing? Do we have that kind of telescopic power? If we set it up in this room, can we shine it up there at the moon?
Yeah.
And see the footprint?
All right, give me a second. Okay, so the moon is approximately 1 light second away.
Okay.
That means it takes light about 1 second to get there. So that means that the moon is 3 times 10 to the 8 meters away. Because light goes 3 times 10 to the 8 meters per second. Okay, so then let's say that a footprint, just to make my life easier, let's say that a footprint is a meter in size, and we can make this a little bit more accurate by making the moon a little bit further away. So let's say that instead of 3 times 10 to the 8 meters, let's say the moon is 10 to the 9 meters, and that a footprint is a meter in size. So that makes an angle of 10 to the minus 9 radians.
Okay.
I need to do this because I need to figure out, because I know how strong telescopes are, but I need to figure out essentially what is the angle subtended
I get
in
that.
our
I
field
get
of
that.
view by this footprint, right? So if something is 10 meters away and it's 1 meter tall, then that means that the sort of 1 meter divided by 10 meters is like the angle subtended. Okay, so we're looking at 10 to the minus 9 radians. Okay, so how much is an arc second? An arc second is 1/360th is the degree, and then you need a 3600th of 360. Putting me on the spot here. So that's going to be 3,000, 300,000, 10 to the minus 6. So milliarc second. So we're on the order of milliarc seconds. So that's going to be really tough from the Earth to see the footprint on the moon. There is nothing that we have in the visible spectrum that can see a footprint on the moon yet.
Okay.
If the footprint were emitting radio waves, then we do have long baseline interferometry telescopes.
What the hell is that?
This is basically if you take multiple radio telescopes and you put them in a gigantic array, you can correlate the signal that you see between these telescopes
Okay.
in order to essentially reconstruct one giant telescope.
Got it. Okay.
This is only possible in the radio spectrum.
Right.
And that's because radio waves have a super long
Right.
wavelength. Okay. So this is how we saw the black hole that we took a picture of
Right.
a couple of years ago. That you can see what are called micro arc seconds, which is a millionth of an arc second. In order to see the footprint, you need to see something smaller than a milli-arc second, which is a thousandth of an arc second. So if the footprints emitted radio waves, so if on the bottom of Neil Armstrong's shoe, you had a little bit of carbon-14,
Okay.
you know, like if he stepped in some dog shit, and dogs eat food, and food, is made of plants, and plants aspirate from the atmosphere, and the atmosphere has some carbon-12 in it, but it also has some carbon-14 because cosmic rays hit the atmosphere,
Right.
and it converts via beta decay some carbon-12 into carbon-14, and so there's some carbon-14 in dog shit, and when Neil Armstrong might have stepped in some dog shit, got on the bottom of his shoe, if a little bit of carbon-14 got on the bottom of Neil Armstrong's shoe, got a little bit in the lunar regolith, and that carbon-14 is decaying and emitting a little bit of radio waves with long baseline interferometry using, say, the Event Horizon telescope that we use to see the black hole, then in principle, we would be able to see it. Unfortunately, the brightness or the intensity of the radio waves coming from that dog shit is probably not
Weak.
bright enough to be able to see it, but the resolution would be enough. We can get pretty close, though. I think with the best...
What about the scooters they left up there? I mean,
they're a little bigger. Yeah, that's what I mean.
The flag and...
Yeah, so all that stuff is on the order of 1 meter, and again, we're in the sort of milliarc second range.
Okay.
So a milliarc second in the visible spectrum is kind of at where like Hubble is at.
Okay.
And so like Hubble can probably see the site that the lunar landing was. So like Hubble might be able to see the scooter.
Okay.
Hubble is a visible space telescope, and so it doesn't have to compete with the atmosphere. It doesn't have to worry about all that. We are building a telescope, or it's like in development, so who knows 30 years from now. It's called the, and they have really boring
$1 trillion later.
Exactly. It's called like it's really boring. Its name right now is called like the Extremely Large Telescope, or something, the ELT.
Okay.
And it's going to be absolutely huge, and it might be able to see milliarc second visible spectrum kind of stuff, and so that might be able to see the footprints. So if you wanted to resolve things on the order of a meter in the visible range, we might be able to do that in like 30 years or something like that. So, but you don't need to do that because we left some stuff on the moon that we regularly interact with.
Okay.
So it's not that...
I didn't know that. What?
So for example, we left this box that has 3 mirrors that all hit each other at a right angle. And the geometry of that shape is such that when light comes in and hits it, it will always bounce back at the same angle. You can work out the geometry that if light hits that at any angle, the outgoing light will always come out at the same angle. So that's very useful. So what that means is that no matter how you hit it, the light will always kind of bounce back at you. So we left one of those boxes, it's called like a corner cube reflector, and we left it on the moon, and we're constantly shooting a laser at it. Whenever the moon is, because the moon is like tidally locked with us, and so whenever the moon comes into view, we are shooting a laser at it. We're sort of following it with our laser. And the reason we're doing that is because it allows us, by counting how long it takes for our laser to get to that little box and to come back and hit our detector, it allows us to measure exactly how far away the moon is, to the millimeter. Because we know the speed of light, and we know to the nanosecond how long it took, and so we can do the math and say, okay, cool, that's how far away the moon is. Why do we want to know that? Because we're measuring how fast the moon is receding away from us. Because the moon is drifting away from us. I don't know if you knew that.
I do not know that.
The moon is drifting away. And the reason is related.
Has it always been?
It always has been.
Okay.
And the reason is related to our time question
we
we're talking about. So the Earth is spinning, right?
Right.
The Earth rotates once every 24 hours. The moon is also rotating around us, and the moon takes about a month, right, to go around us. That's month, M-O-N, and month, moon.
Yes.
The same thing, right?
Yes.
But moon takes about 29 days to go around us. Those periods are not in sync with each other, right?
They would, they couldn't be.
Right, exactly. One's faster than the other one. So what happens is the Earth is like a sphere, but the moon causes it to sort of bulge a little bit. That's what causes the tides, right? It takes the world to the world's oceans and then makes them bulge just a little bit. So whenever you're on the shore, it makes the water level change a little bit. So the Earth is rotating, which is causing that bulge to not exactly point at the moon. So the bulge wants to point at the moon because the moon is pulling on it, but the rotation of the Earth drags the bulge a little bit and causes it to be a little bit in front of the moon.
Okay.
That bulge subsequently pulls back on the moon, and what that does is it couples the Earth's rotation to the rotation of the moon.
Got it.
And it drags the moon along. And so what we're doing is we're actually speeding up the moon. We're like flinging the moon forward with our rotation.
Okay.
So we're giving the moon energy,
right,
which is causing it to go into a higher orbit.
Got it.
And subsequently, the moon is stealing energy from us, which is causing us to slow down our rotation. So a month is getting shorter and shorter as the moon gets further and further away. And a day is getting longer and longer as the Earth slows down.
Got it.
And this will keep happening until they're exactly in sync with each other. And a month and a day will be exactly the same length of time.
Which will be approximately when?
Like 5 billion years from now. Or super long time. But one that
not next week.
Exactly. When that happens, the moon will be at exactly the same point in the sky all the time. So one side of the Earth will see the moon, and the other side of the Earth will never see the moon.
Okay. Another random question. This is very elementary, and I probably should know the answers, but I do not. I've always wondered how this multi-ton thing of steel takes flight. And at what point can I drive my car, throttle my car as fast as I can? At what point will my front tires go off the ground? Like, how do we scientifically define what it requires to make something airborne? But I just never really understood how it's possible for something that big and that weighty to take flight.
It's really mind-blowing.
And are you going to give me an answer that also explains the following? I take a bowling ball, I take a marble, I drop them, they fall at the same rate. I guess that was Newton's thing, right? But a feather doesn't fall that speed. So what is the differential in the feather, like mechanically, what has to be taking place in terms of measurement that requires that the item will drop at the same rate?
Yeah, I think a really important thing to remember, which can be hard to remember, and was definitely something that the ancient Greeks didn't think enough about, and which is why Aristotle got a lot of things wrong whenever he was trying to think about science, is that
he gets maligned a lot, doesn't he?
I make fun of him a lot. Yeah, definitely. He's definitely the bad guy in all of my classes. Yeah, which he's like one of the founders of science as like a field, so I shouldn't. But we should all just accept the fact that we are like little crabs that are living in the bottom of a very deep ocean, right? That we are not on like the surface and there's like a sea that is like, you know, the Atlantic Ocean, the Pacific Ocean, that we are at the bottom of this 100-kilometer ocean called the atmosphere. And that there is a more dense ocean that we go swimming in sometimes, but that there is this other ocean, this bigger ocean called the atmosphere that we are already on the very bottom of.
But that atmosphere is less dense the more you go up, is that right?
That atmosphere does get less dense the more you go up, but that atmosphere nonetheless is a very important dynamical fluid that we can interact with, that we can push off of, that interacts with us.
Fluid.
It is a fluid. It flows just the way that like a liquid flows, right? Yeah. And you might not really notice it, but that's because you're sort of in the middle of it. So for example, that atmosphere is, you know, it's every box, every 1 meter by 1 meter by 1 meter, so 1 yard, basic cubic yard more or less box of that atmosphere weighs a kilogram.
Okay.
Right? And it might not sound like a whole lot because a cubic yard is a pretty big box. But if you think about it, a 10 yard by 10 yard by 10 yard sort of like room is 1,000 cubic yards. So there's 1,000 kilograms of this fluid inside of that room, right? And so if you go 100 kilometers up in the air, there's a lot of that stuff on top of you. How much of that stuff? Every square inch of your body is being compressed with 14.7 pounds of pressure.
Okay.
That pressure is called atmospheric pressure, right?
Atmospheric pressure.
That's what's pushing on you. And you might say, well, how do I not get crushed, right? 14 pounds, 14 pounds, 14 pounds, 14 pounds. That means there's like thousands of pounds pushing on me at all times. Well, it's because inside of your body, there's thousands of pounds pushing outwards as well, and so all that stuff sort of cancels.
Because gravity's kind of weak, right?
Gravity is pretty weak. Yes, that's true. We can get into that side of, but just to kind of stay on like the pressure fluid train for a second, because the gravity being weak train is a whole other train that we could pop onto as well. But yes, so there's this fluid, and we don't think about it much, but it's there. And if all of a sudden I snap my fingers and the fluid was gone outside of your body, you would literally explode. Because that 14.7 pounds per square inch that's inside of your body would just explode out of your body, right? And so anyway, so it's there. And so you should always be thinking about that whenever you see this giant metal plane sort of taking off and go through the sky, and you're like, how the heck does that happen? When you see feathers take forever to get to the bottom, and how does that happen? Right? You should be thinking, okay, I am like a fish that's in water. And so, of course, things are able to sort of like fly through the sky. Of course, things fall weirdly because in water, you see whales like floating around, right? It's just the density is a little bit different.
Got it.
And so the dynamics are a little different. You need to be shaped a little differently. You need to be moving with different speeds and stuff like that. But nonetheless, there is still millions of tons of this stuff that we're able to sort of push off of and be buoyant with respect to and things like that. So, your initial question, I have a car, and I want to just drive until I start going off into the air, right? So that is definitely a thing that can happen, and that's why there are things like spoilers on the back of cars, which are shaped like an airplane wing, except upside down. Why an upside down airplane wing? Because they don't want to make the car go up off of the road. They want to make the car be pushed down onto the road in order to increase the amount of friction that the back tires have onto the road, right? So it is possible for cars to kind of obtain a speed that makes them kind of fly up in the air. And you sometimes see in accidents with like Indy cars and stuff like that. You see them like kind of go flying, right? And that's not a big surprise because an airplane on a runway, how fast is an airplane going whenever it takes off? Not much faster than my truck in that calculation I just did, right? It's not like airplanes are going like 300 miles an hour whenever they take off. Airplanes are going maybe like, 80, 100 miles an hour. Like they're going as fast as you're going if you're speeding on 79 at like 2 o'clock in the morning. So it's not their speed that makes them take off. I mean, they do need to be going fast for sure. But what's more important is their shape, right? So airplanes are shaped in a certain way that they generate what's called aerodynamic lift. That speed creates lift. So how does that speed create lift? There's this really cool principle that's called Bernoulli's principle, and it's the following thing, that if you have a sort of surface and you have air that's blowing over the surface, if air is going faster on one side of the surface than the other side of the surface, then the pressure will be lower on the surface that is faster moving air, right? That the pressure is actually sort of inversely related to that speed. That the faster the air is moving, the lower the pressure is. And so what that means is that if you have low pressure up here and high pressure on here, you should think of the pressure as like this contest where the pressure is pushing like this here and it's pushing like this here. Mm-hmm. So low pressure, high pressure, that means one side wins and it pushes up. That's why a roof blows off of a house during a hurricane. It's not that the air gets like underneath the roof and then blows it off. What's happening is that the air moves over top of the roof, and that creates low pressure. And then inside of the house, it's like your body, where all of the air in the room disappears. 14.7 pounds per square inch inside of the house now have nothing to fight against, and then the air inside of your house explodes your own roof.
Okay.
That's why you open your windows, because you want to let that air get out of the room without blowing your roof off. Do you know what I mean? And so that's essentially what airplanes are taking advantage of. Their wings are shaped in a way such that when the air moves across the wing, it goes faster above the wing than it goes below the wing. So that creates low pressure above the wing, high pressure below the wing, and that pressure pushes on the bottom of the wing. Now, your car is not shaped like...
It's not aerodynamic.
It's not it's aerodynamic in a different way. It's trying to reduce its drag. It's not trying to increase its lift. Right?
It's reversed.
So it's definitely not attempting to fly.
What about
a
conventional Apollo spaceship? Like, there's no wings on that.
Yeah, so a spaceship, it gets out of this 100-kilometer sea that we're in as quickly as possible, and then it's in space. And so it doesn't have to worry about that at all. Now, the space shuttle did have to fly a little bit, and so it had wings, because it had to enter and exit the atmosphere a little bit. But a typical spaceship, it's trying to get out of this ocean and get up into space where there is no air. And so it was trying to avoid the air.
The turbines in the engines on the wings or on the back of the tail,
I guess,
on a commercial plane, that's what's propelling it.
Yeah.
And the louvers on the wings determine the height and the speed.
Yeah,
of the
the
plane.
pitch and the yaw and all those sort of things. The speed is determined by the turbines, which are basically taking in air, and then that air is mixing with the fuel, and then it's exploding inside of there. And
That's
then,
horrifying.
And then that explosion is basically like it's getting compressed as it goes in through the turbine, and it's heating up, and then whenever it gets hot enough and it gets mixed with the fuel, it explodes.
Okay.
And then that explosion creates a massive amount of thrust in one direction. And so the exhaust goes in this direction, and the thrust goes in this direction. And so that pushes the plane forward.
Right.
And you could increase the amount of fuel, you can decrease the amount of fuel, and
that's what that. So that's actually like increasing the fuel injector in a car. I mean, it's like pressing on the gas.
Yeah, that's the gas pedal. Yeah, exactly. And so that's increasing the thrust of the turbines that are spinning that thing. So that's increasing the speed. The little louvres are basically changing the shape of the wing so that you're changing the sort of direction of that aerodynamic lift. So is the lift like in this direction, or is it in this direction, or is it in this direction? And it'll cause the plane to sort of tilt forward, backwards.
So that's how you steer the plane.
So that's how you steer the plane. And you could do the same thing where you could kind of do this too, the pitch and the yaw and all that sort of thing.
Talk a little bit about the difference between a jet and a propeller.
Yeah. So a jet
engine
has these turbines where the air comes in, compresses, mixes with fuel, and explodes, right? So that's like a jet engine. Propeller basically is like an internal combustion engine where it's just a normal like car engine type thing that turns a drive shaft. But that drive shaft, instead of rotating wheels, is rotating a propeller. And so what is that propeller? That propeller has a whole bunch of little wings on it, and then those little wings themselves create lift, but instead of the lift picking the plane up like this, the lift is a force in this direction.
So it goes forward.
So it pushes the plane forward.
So there's the wings also have the louvers that do the same thing as the jet plane does.
Yeah, so they steer the same sort of way. It's just that they kind of have two different forms of aerodynamic lift. There's once the plane's moving forward, The air coming over the wings creates lift that picks the plane up and allows it to move like this. But then what makes the plane move forward in the first place is the propeller has a lift force that pushes the plane forward.
Okay.
Okay. The jets work differently. They have a motor that sort of moves the wheels just like a normal car until it gets up to cruising speed, and then it has these turbines that kick on that create these exploding forces that push the thrust
Using
forward.
the word explosion in an air flight is terrifying to me.
Look, this is one pitch. If you weren't convinced about weaning off of fossil fuels yet, here's a pitch right here. Do you really want a controlled gas explosion happening inside of your vehicle?
Yeah. Well, has the concept of electric airplanes even been floated?
It absolutely has, but we are really far away from that. Unfortunately, air flight is going to be, I think, one of the last things that we're going to be able to successfully
even for like small planes.
Yeah, I mean, at the end of the day, like I was saying about it's all about energy density
And weight.
Yeah, in a car, like you can make your car 5,000 pounds. And it's like, like I said, a Model 3 is like 5,000 pounds. A Civic is like 2,000 pounds. Right. You can more than double the weight of your car, and it's not really that big of a deal because at the end of the day, the cross-sectional area of the car is the same, and that cross-sectional area determines your aerodynamic drag.
Okay.
Right? And the friction, you do get a small increase in friction from the wheels if your car gets heavier, but it's not that much. It's not like, it's not like a semi-truck has like that much insane amount of friction because it's like 10 times heavier, right? So with things that are rolling on the ground, you can double, triple the weight of your vehicle, and it's not like all of a sudden you like lose like a ton of efficiency. With airplanes, you can't just fill half of the airplane with lithium ion batteries and make that economical. Like, it's just not going to work. Like the airline industry is already extremely lean whenever it comes to its profit margins.
Oh, yeah.
And if all of a sudden you lose
half the seats,
half the passenger capacity because you need to fill that with
could
something.
they do it?
Oh, you could do it. You could just make flights cost like $4,000 or something.
So here's I'm playing devil's advocate for a second. If that is possible, then why is our military not using it for different for military applications? Not passenger planes, but for war instruments of war. Is there any advantage to the electric engine when it comes to outside of efficiency, but maybe in terms of speed or maneuverability?
I definitely think the short answer to that is definitely not for like a fighter jet or something like that. Yeah, no, definitely.
Why not, Coop?
Just
weight.
Yeah, I mean, like you want this thing to be the highest energy density possible is basically jet fuel engine. I mean, that is like super high energy density.
See, I guess I'm confused, like, because everybody talks about like what I literally almost had my neck broke in a Tesla.
Yeah.
And the driver was showing me from 0 to 60 at some reason. So
yes,
it was so powerful.
Yeah.
That you're saying it wouldn't translate to a fighter jet.
Right. If we still used propeller planes, then it would translate, because electric motors are extremely good at generating rotational torque, which is why Teslas are able to accelerate so fast.
Got it.
But the way a jet engine works is by taking this compressed air, heating it, and exploding this jet fuel. That is a completely different mechanical mechanism to create that thrust. So it's very different than the way that electric motors work. Basically, you have to go back in time from a jet engine to a propeller engine to go from fossil fuels to electric engines.
Same concept. So am I safe to say that the reason why we went to nuclear submarines and nuclear powered boats was because of the weight? We didn't need to.
So nuclear fuel is to gasoline what gasoline is to lithium ion. What I mean by that is the same way that gasoline is way more energy dense than lithium ion is, nuclear energy is way more energy dense than gasoline. So like why we use nuclear submarines is because you could have a baseball worth of nuclear fuel, and that will be enough fuel to last you for like 10 years. Like, it's just an absolutely insane amount of energy.
Devil's advocate, why are we not developing engines for cars with this tiny little amount of plutonium or whatever they use, and then because in theory that might equate to running that car forever.
Yeah.
Right?
Yeah. In principle, if people were a little more comfortable with there being plutonium inside of their car, we could make cars that you would basically buy, and then they would have energy for the rest of their lives. Is the technology
here?
Probably not yet to do what you want to do for that. So, for example, the Mars rovers, all the rovers that like Curiosity and the most recent rover as well, all the Mars rovers are that. They use what's called radioisotope thermoelectric generators.
Okay.
So they basically have a radioactive isotope. It's usually some kind of plutonium. And they have a device that, given heat, it can convert heat into electricity directly.
Okay.
So not via like boiling water, creating steam, using steam to turn a turbine, or the way that like we usually do. It literally just creates a voltage from heat. And that's how these rovers work. Because on Mars, the light is a lot dimmer because you're further away, so you don't get as much solar power. You don't want to have to carry around a giant solar array. Like, you want to be able to drive around, and you want to be able to work at night. You want to be able to work during a dust storm, stuff like that. So they actually have these radioisotope thermoelectric generators on board, and yeah, they run for like 20 years, and they can just like drive around with basically.
See, to me that
fuel.
Sounds like that's the solution.
So yes, but where those are at right now, first of all, they're very expensive, because you basically need to like create this brick of plutonium, which you might not want people to be able to go to Ace Hardware to go get. And also, it's pretty low wattage. Like, the way that these create energy from heat is still like maybe on the order of like a few hundred watts.
Okay.
So call it 500 watts, right?
Could that power a car?
1 horsepower is 750 watts.
Oh, wow.
So
we got a problem.
So 200 horsepower, which is like a Honda Civic, right? So what is it? Yeah. 200 horsepower would be 10 horsepower would be like 7.5 kilowatts. And so, yeah, you can kind of do the math. We're talking like way, way higher. So we're on the order of dozens of kilowatts. Yeah.
So does that mean you would need more plutonium, or you would need different technology?
It means that we probably would need a better technology. I mean, like, because these work for submarines. Submarines use dozens of kilowatts in order to run, right? And so clearly it's possible. They just don't use this specific technology that's inside of the Mars rover. The Mars rover doesn't require that much power, so it doesn't require this whole entire thing. Submarines and aircraft carriers, they're able to have an entire like water boiling, steam creation, energy generating thing on board, and so they can generate energy the kind of more traditional way. So they don't use this very low efficiency heat method, right?
Okay.
We don't want to put a whole power plant inside of a car, and so we need something in between. We need something that would use nuclear heat, because that's what nuclear energy is. It's just like a rock that gets hot because it's decaying.
Right.
So we need something that can turn heat into electricity that's not a whole entire power plant, but doesn't use this like inefficient quantum Hall effect thing that this radioisotope thermoelectric generator uses. So there's probably something in between that we haven't figured out yet. But in principle, yes, like uranium's energy density, all of America's energy consumption, heat, transport, commercial, electricity, everything, in 2020 was about 100 quadrillion BTUs of energy.
Okay.
Right? So in terms of scientific units, that's about 10 to the 20 joules of energy.
Okay.
If you convert that into just cubic meters of uranium, it's like maybe 300 cubic meters of uranium. So that's it. So that's a pile of uranium that's like 10 meters by 10 meters by 3 meters. So that's 30 feet by 30 feet by 10 feet.
That's insane.
So that's like a room of uranium that's like maybe 3 of these rooms. And that's for all of America, right? all of our energy, heating, cooking, driving, flying, like commercial, every single thing. That's how rich and energy dense uranium is. That's why nuclear is like a really promising energy source if we could just figure out how to make it economical. I think the real problem with nuclear is that it's just like, it's not super cost competitive. It's a very
So we haven't refined the technology well enough yet.
Yeah, and
there's public fear about it, obviously.
There's a lot of that. Yeah, I think there's a lot of unwarranted public fear about it, but it's also just like there's a lot of cost overruns in nuclear projects that are silly. I feel like
when they say spent cores, they have to store spent cores away. So what is the residual? With nuclear in general, how do you explain the residual byproduct?
Yeah, there's nuclear waste that decays and becomes not dangerous after a certain amount of time, and then there's like the long-term nuclear waste that's like bad for like 10,000 years. That's usually the stuff people are like really concerned about. So
what's the most efficient way to deal with that?
And the most efficient way to deal with that is to literally just bury it in the ground.
Okay.
And it's not that stuff, you can cover it in like just a little bit of lead, or you can cover it in like a couple feet of concrete, and then you could stand on that concrete pad and it's completely safe. The only thing that's tricky about it is that it, like I said, 10,000 years. And that's like what makes people like kind of freaked out about it, is like, yes, it's not very much. Like I said, 10 meters by 10 meters by 3 meters. Okay, that's for all of our energy consumption. That's pretty good. That it's not very much, and only a certain fraction of that becomes the high level waste. So imagine pretty much like the size of this room becomes high level waste for an entire country the size of America.
That's amazing.
So that's not a whole lot. And if you think about it, renewables generate waste too. Like what happens to all those solar panels? What happens to all these wind farms? And where does that waste go? That waste is distributed all over the planet. It gets thrown in landfills here and there, and that has tantalum, that has all sorts of heavy metals in it. Like at least nuclear waste is contained and we know where it is, and we could put it somewhere. Like waste from other things gets distributed all over the place.
Right.
Waste from carbon dioxide gets smeared out all over the atmosphere. Waste from solar panels gets thrown in landfills like all over the world.
Right.
Waste from nuclear, we know exactly where it is. It's in these containers, and we could like locate it and keep track of it. So anyways, I think the waste problem is actually easier to solve with nuclear than it is with any other technology, even though it is a long time, and it's actually pretty easy to like seal it. It's just that people get like really uneasy about like, well, we can't even conceptualize what it means to like keep track of something for that long.
Right.
And so people are talking about like burying it inside of a mountain. People are talking about like digging like huge cores. Finland has a whole mountain that they built a mine into, and then they dug these cores into the mine, and then they're filling these cores with this stuff and then sealing off the mountain. And so,
well, I mean, it sounds like a workable solution.
yeah, we're pretty good at mining these days, so it's really seems pretty good to me.
Okay.
So honestly, I don't even know if it's worth it to do that, though, because in the future we might come up with the technology that can use that waste to generate more energy.
To use it.
And so, like, I think that honestly we should put it in a warehouse and just guard it, like, I don't know, Fort Knox or something. Like, it's not that much.
Yeah, bank on our future potential.
Yeah, put it on an island, save it for something. I don't know. Yeah.
Okay, so the last question I wanted to ask you might put you in an interesting spot, and if it doesn't, something you don't want to answer, that's fine. But I think I can ask this question of an economist, or I can ask this question of a scientist. I think it's better asked of a scientist.
Okay.
I'll tell you why. And the question is, can you give a layman's answer of what this cryptocurrency is, and when people say it's bad for the not economy, well, that's debatable, but it's bad for the environment. That freaks people out. Like, how can a currency be bad for the environment?
Yeah.
I think I understand some of it, but
sure.
Can you give the layout of what it is, why it's a thing, and what are the benefits and what are the detriments?
Yeah, I have a lot of opinions about cryptocurrency. Okay. So I'm happy to. Again, this is Coop Steak.
Coop Steak. We're going to start naming these episodes Coop Steak.
Coop Steak. Yeah, this is theoretical physicists talking about cryptocurrency for some reason. Right.
Right on.
So cryptocurrency. I mean, this kind of started with this like this paper that came out by this guy. Satoshi Nakamoto, I think, something like that.
He's still around?
It's a fake name. So nobody knows who this guy is.
Fantastic.
It's like a secret guy.
Oh, really?
Yeah. So it's like people aren't really sure who he is, or
That's
like
crazy.
not a lot's known about him. And it was maybe 2008, 2009, something like that. It was kind of like between 2005, 2010, and it was for a protocol for creating a cryptocurrency, which is basically
What is cryptocurrency?
What is cryptocurrency? So how do currencies work? Basically, if you want to make some sort of exchange, you could have a barter system where it's like, I'll make a pair of shoes, you give me a donkey, here's some shoes, give me your donkey. But that is not a very useful way of creating an economy, because if I need a donkey and you don't need a pair of shoes, then I need to find somebody that needs a pair of shoes that has the thing that you need, and we need to mediate that. What would be better is if we can create some sort of third thing
Intermediary.
that had value, that I could just say like, okay, these shoes are worth this third thing, that donkey's worth this third thing, and we can just make this exchange for that third thing, and then you can use that thing to get what you need, I can use it to get what I need, right? So that's kind of what created these currencies. And so what currency we have today is what's called a fiat currency, which is a currency that's not really based off anything except for just the mutual trust of the society that we live in, right?
It's not gold in Fort Knox.
It's
That's
not
what we're all
gold
led
in
to
Fort
believe.
Knox, right? And that was done in like 1971 or
Not
something.
really sure there's any gold in there, to be honest.
Exactly. Who knows, right? So this was like Nixon, like 1970s. We decided that we're no longer going to base it off.
That's all you have
gold.
to say.
Yeah, you can go from there.
Tricky Dick.
Exactly. So it's no longer, you can no longer say that like $1 is worth this many ounces.
There's
of
no
gold.
gold standard.
There's no gold standard.
Right.
It's basically a free floating currency, and it's just a piece of paper that we all just kind of say. A way to think about it, Warren Buffett described these things as like a IOU from society. That basically it's a piece of paper that is written from society that says, I owe you 20 something worth of goods and services.
Okay.
So a $20 bill is like a piece of paper that society gives you that says you can go into society and get $20 worth of something from them. Like you can get $20 worth of gas, $20 worth of food, a giant eagle, whatever, and society will pay you back because you did something for society, like you worked at a university or you sold a house or whatever, right?
Okay.
And so these are just a bunch of like IOU papers that you have, right? Okay, so what sort of like justifies their value? Well, that's like the U.S. government, I guess. And so you kind of have to have faith in this like central governing body that they're not going to just write a
We
whole...
call that the Fed.
Exactly, the Federal Reserve. Are they going to like write a whole bunch of IOUs, like print a whole bunch of IOUs so that way like a whole bunch
Not
of
us.
people
We
have
haven't done
these?
that, have we?
No, never, of course. We haven't done that in the last like 6
2 weeks.
months. Yeah. So basically like in order for this to work, you kind of need to have some central system that's making sure that, one, they're enforcing that people accept this fiat currency, and two, that the sort of supply of this currency stays limited so that way the value of this currency maintains its nature, right? Mm-hmm. And so how could you create a sort of decentralized, so without some sort of central body, currency? And that's what this Satoshi guy came up with. It's like, what's the sort of protocol that you could digitally have some sort of ledger that kept track of how much money, digital currency, digital money everybody had? It's just like a number associated to everybody, but where everybody knew how much everyone else had, and whenever you want to make a transaction, everybody sort of verified that, like, yes, that transaction happened. Your amount of money went down by
so
this
I didn't
much.
know that. So
his amount of money.
Your balance is disclosed to everybody else.
Yes. Now,
That's interesting.
Yeah. So in a sense, it's kind of more open because
It's a little unsettling.
Yeah, all Bitcoin transactions are public knowledge, but it's also less open because it's not that like the name like Eric McKenna is next to some dollar amount. What it is the public RSA key next to this Bitcoin wallet is what's sort of
I'm
public.
not identified.
But
with it.
you aren't necessarily.
Got
There's
it.
nothing. So you might have various Bitcoin wallets in your computer.
Got it.
And you could give those RSA keys to whoever you want, and those can be exchanged or sold or whatever. There's nothing tracking those RSA keys, right?
How do I claim them then? What's my claim to them?
Basically, if you have the private RSA key, which matches that public RSA key, that's essentially like the password to the account that
Okay.
allows you to take that, allows you to make purchases with that
Okay.
money. And so if you lose that password, then that money is gone.
It's kind of sketchy.
So this happened to my roommate. actually, in graduate school. My roommate, she got in on the ground floor of this stuff because she was a computer scientist. So like totally had no interest really in like Bitcoin from an economics point of view, just like she was into computer science. She heard about this thing, read this paper, thought it was cool, and her computer was mining Bitcoins back when it was extremely easy to mine them. And so she had several Bitcoin, which are now worth like, what, $50,000 each. And so she got them completely for free because she was just mining them. It was really easy whenever you could buy a pizza for like 1 Bitcoin. And her Bitcoin wallet was on this laptop in our apartment in Brooklyn, and somebody just broke into our apartment in Brooklyn and just like stole the laptop, stole a bunch of stuff. And
are they passwords you could keep them manually, or they're just
you could,
long strings of numbers?
They are long strings of numbers. You could keep them manually. She could have had it backed up. At the time, like Bitcoin really wasn't worth that much anyways. It was maybe like $10,000 worth of Bitcoin on there, which she didn't pay for. So it wasn't like she like lost out on an investment or anything. But she was just like, shit, I didn't have that backed up on anything. The person who stole it, I'm sure, immediately pawned the laptop for like $100 and didn't know anything about it. But nowadays, that was probably like maybe upwards of $1 million worth of Bitcoin.
Oh my gosh.
So anyways,
that's brutal.
Very sad. But anyway, how does Bitcoin work, and why is it environmentally unfriendly? Well, how is a currency environmentally unfriendly?
That's where I'm confused.
So in order for this sort of transactions to kind of work, is you need to be able to sort of, when you make a transaction, you lose some money, and in order for the system to work, you need to not be able to like go make another transaction before the system sort of realizes that you lost that money. That's like a really hard part about cryptocurrencies.
No,
like,
how to follow.
Like if this is a decentralized system,
right, that
means that everybody in the network needs to keep track of the ledger of like who has all the money. And so that means that like I have $100, I buy something from you for $20. It takes time for us all to agree Coop just bought something for $20. So I can't like buy something from you for $20 with my $100 and then right after that go buy something for $100 and say, look, your ledger says I have $100, doesn't it? Because it'll take you time to realize, right? There's some latency there. And so in order for everyone to get into sync, there's this blockchain technology that basically it has this like proof of work algorithm, which basically has purchases go onto a block. And then in order to verify the purchase, your computer needs to do some sort of computation. That's what mining a Bitcoin is your computer's doing a computation which verifies the block. And then that computation is so computationally difficult, and it gets more difficult the more people that are on the system, that it literally just takes time to do. No matter how fast your computer is, it takes time to do the computation. And in that time it takes to do the computation, everybody can kind of get on the same page, and then that block gets verified. And then there's a whole song and dance about like the longest chain of verified blocks becomes the sort of canonical like chain. Anyways, it gets kind of confusing, but the point is that this step of verifying a block and adding it to the chain, what you're doing is you're essentially just like crunching a bunch of numbers on your computer, and it's intentionally made difficult because it's intentionally made time consuming, because you're intentionally giving time for this ledger to get everybody on the same page so that people can't like spend money they don't have.
Got it.
And it just takes an enormous amount of energy to verify these blocks, because of the fact that so many people are using electricity.
Like computer broke time.
Computer time, yeah. And because so many people are on the network, you need to verify so many of these blocks. And what's the incentive to verify the blocks? Like, who verifies it? Well, to incentivize it, you get a couple pieces of Bitcoin, like maybe like 1/1,000,000th of a Bitcoin or something for verifying a block. And so that's how you get rewarded. That's how you mine a Bitcoin, is you verify a block. And so there are all these Bitcoin miners out there who are doing the job of verifying the blocks, who are essentially the Fed. They're doing the job of making sure everyone's on the same page about what the ledger is. And for that, they're being rewarded in Bitcoin. But in order to verify all these blocks, they need to sit there and have like thousands and thousands of computers just crunching numbers all day, which is just taking an absolutely astronomical amount of energy.
They're spending more. Are they spending more of their personal money in energy costs than they're earning in Bitcoin?
It turns out that the calculation, it depends on where you are. And so a lot of these massive Bitcoin mines are like in Iceland next to geothermal plants, where like these giant geothermal plants are able to create so much excess energy during times whenever the like Earth is very active that they would throw that energy away anyways, and so they can like take that waste energy for very cheaply, and then they could like mine a whole bunch of Bitcoin during that time.
This sounds so sketchy to me.
It's totally crazy, right? And there's like, you know, coal energy in the western provinces of China is really cheap, and so there's a bunch of there were a bunch of Bitcoin miners
bunch of
there.
Mainframe computers that are just mining Bitcoin all day.
Yeah. Yep. And you can do it at home, and it works out to be still somewhat profitable. We did the calculation at this nonprofit community center that me and my friends founded and work at in Wilkinsburg called Community Forge. We have this program called Boot Up, where we kind of teach kids how to use computers, about 21st century technology, coding, cryptocurrency, everything. We have a little Bitcoin mining setup as just a little demonstration of like how the technology works and everything. And it actually generates I think it maybe generates something like 60 cents a day or something like that. And that's it after you subtract the cost of the electricity. So it actually is profitable even, you know, at the price of like 8 cents per kilowatt hour, which is about how much energy costs in southwestern Pennsylvania. So it does depend on energy costs. It depends on how efficient your machine is. It depends on how many GPUs your machine has.
So to generate, like,
it depends on the cost of Bitcoin. That fluctuates as well.
Okay, yeah. So you probably can't give me an answer to this question, but I mean, like, to make $2,000 a month doing it, you need some serious hardware.
Absolutely, yeah. That kind of money, you would probably need to get like $10,000 worth of hardware or something like that,
and just let it sit and run all day. Do you have to do anything to it once you start it? It just goes.
Yeah, once you start it just goes, and that's why it's something that's like kind of cool. Is because if you have a really nice gaming computer, the same technology that's good at mining Bitcoins is really good at running like Skyrim and like really intense video games and stuff. And so if you have a gaming machine at home and you're not using it, like if you've spent $2,000 to get a super nice 3080 graphics processor, then might as well have it mine Bitcoin whenever you're at work or something like that.
Well, talk to me about computers to a degree, just from a novice standpoint here. Hard drives, traditional hard drives with a disk would wear out. SSD drives, theoretically, there's no moving parts in there. So is there anything, can a computer wear out?
Absolutely. I mean, they have life cycles for sure. But this is basically, there aren't any moving parts in the processor itself. And so this is just using processor power. It's not like, the reason why like a hard drive wore out before is because literally like a motor was like spinning a disk, and so there's like a mechanical thing happening. Yeah. This is literally like running numbers via electric fields, via voltages through a central processing unit and like a graphics processing unit. And so of course these things they don't last forever, but like that probably wouldn't be the first thing to go with your computer. Like, technology is changing so quickly that usually your machine becomes obsolete before it becomes not functional. You know what I mean?
That's interesting.
So like, you can use it as much as you want, and before it sort of wears out from use, it like stops being useful, where like new software won't run on your machine. Even though your machine's perfectly good, it just can't get updates anymore.
It's fascinating to me. You're saying if I go buy $10,000 worth of Apple equipment and I start running Bitcoin, I actually can make a couple grand a month.
You might, yeah. It wouldn't be Apple equipment for sure. You would have to basically build
PC-based. Yeah,
you would build stacks. I mean, basically, you might want to build like a Linux machine, basically. You would want to get like stacks of graphics cards, basically, that attach to a motherboard. Yeah. $2,000 a month, you'd actually probably want maybe more than $10,000. But in principle, yeah, there's investments. People definitely work out the math on that, and you can.
And once you start it, you don't even have to do anything to it. You just put it in the corner and just let it go. Is there any maintenance involved?
So one thing, yeah, like your fans, I think you want it to be kind of in a pretty clean room. Your fans are basically running 24/7,
right.
on your motherboard. But
Like a mainframe room. Like companies have mainframe rooms that were like it was cold and temperature controlled and humidity controlled and all that nonsense.
Yeah. I mean, a lot of people do this. This is a very common thing. People rent apartments where the only thing that they have in the apartment is just a bunch of computers, and they just pay electricity bills, and landlords get very annoyed because it's hard on their like breakers if they're like running, because like the breaker in your house is not designed to be at load all the time, right? Like if you have like a 25 amp breaker in your house, it's expecting to be at like maybe like a couple amp continuous, and then whenever you have the vacuum cleaner on, it's at 10 amps for a few seconds, and then it's off. And when the microwave's running, it's at like 4 amps for a few seconds, then it's off. But if you have a array of GPUs running, or something,
it just seems nuts to me. Like, but I can see someone buying a piece of property, a small little house, self-contained house, putting a 200 amp service into the house, and just loading it up and just letting them just go block. Is it called blockchain?
Blockchain is the general framework for this technology.
Bit mining.
But yeah, mining Bitcoins, mining Ethereum, mining Litecoin. Like there's a billion different kinds of these coins nowadays.
Like what do you mean? But I don't understand. How can there be different coins?
There are just different kinds of digital currencies that use different protocols, and there are different marketplaces for them. Just like there's euros and dollars and yen and Swiss francs. There's Bitcoin. There's Ethereum.
All right. So if I was to invest in Bitcoin, like if I was like, is that done on an open market? Like
yeah, you can go and buy Bitcoin, and you could sell Bitcoin, and you can take. There are Bitcoin ATMs. You can take Bitcoin out of an ATM now.
It's just a ledger. You're just pulling out a ledger that says you have this amount of money.
More or less, yeah. I mean,
there's no cash. There's no tangible thing. There's no coin.
There's no actual coin. That's right. Yeah. So it's kind of similar. I mean, nowadays, like I don't really use a whole lot of cash anyway. So
I don't think anybody does.
Exactly. So it's not like hugely different than the way that I interact with money on a day-to-day basis, anyways.
What's your overall thoughts on it?
Overall, I'm not a huge fan. I do like this sort of idea behind the technology, because I like this sort of digital authentication, decentralized nature that it could lead to new kinds of like cooperative economies that allow for like, one thing that I saw was kind of cool is like ways to create shares in cooperatives, like artist cooperatives, and ways for like musicians to create platforms that are owned by the musicians instead of owned by Spotify and stuff like that. These kind of things I think are really cool projects. In terms of just cryptocurrency generally, I do like that like a 12-year-old kid can get some digital money and can like have like, because it's really hard for like 12-year-old kids in like say Wilkinsburg to like get a bank account, for example, or like 15-year-old kids get a bank account. Like some of the youth that we work with in Wilkinsburg like have to like hide their money from their parents and stuff like that.
Right.
And so they can't like go with their parents to get like a bank account for like to put their paychecks into with their like summer jobs through the programming they do with us. And so like Bitcoin is kind of an interesting alternative for that. There's no sort of like guy in a suit that's going to tell them they can't open up a bank account or they have to pay fees because they don't have enough money in their account or something. It's totally, so that's kind of chill. So there are some sort of like interesting, liberating, not controlled by the man aspects of it that I like. But one thing I do worry about is that I think one of the largest social problems that we have, and I think the Pandora Papers just exposed this even more, which is just kind of like
what were those?
Have you heard of the Panama Papers?
I have not.
Okay, well, the Panama Papers was this huge data leak that happened a few years ago that exposed all these offshore accounts where rich people were evading taxes.
I think I heard of it. I didn't dive into it.
Yeah, so this was one of those. Pandora Papers was just this times 10 that just happened recently, where basically some journalists got their hands on over 1 million pages worth of documents of just rich people, kings, celebrities, just having like
untraceable money
in the Cayman Islands, buried. And all over. Yeah. And so to me, one of the biggest social problems that we have is that inequality is just making it extremely hard to create cohesive societies.
No question. No doubt.
And tax evasion is really hard. I mean, like whatever your opinion about taxes are, people that should be paying them, right? Like people, like even if you think taxes should be lower on some people, the taxes that they do have, they should be paying those ones, right?
Right.
And people are even able to get away from those. And I think Bitcoin just makes that problem even harder. Whenever you have an international currency that no nation can sort of create any sort of taxes on.
Well, that's the problem. The governments are terrified of it, aren't they?
Yeah, and that's why like China is making Bitcoin completely illegal. You can't even mine Bitcoin in China. Like you can't even at your house mine Bitcoin in China. Yep, they just made it completely legal. But they also created their own digital currency that is because they see some of the benefits of a digital cryptocurrency, but they at least want to be able to kind of like regulate it. And so they created their own like cryptocurrency, like the digital yuan or whatever. But yeah, all those Bitcoin mining things in Western China are like shut down now because it's illegal in China to mine Bitcoin.
Is there an attempt to moderate the thing in some way?
That's what people are trying to figure out. Like, how can we kind of come to an agreement where it's like, Bitcoin's cool. Is there a way to like attach people to these Bitcoin wallets so that way you won't be able to evade taxes? Like, is there a way to, just somehow help so that there isn't a way? Yeah. And
when you go out and you mine for a Bitcoin, who set up these? It always goes back to somebody. Who set up the control that you get awarded these extra Bitcoins for this amount of computer effort? Like, who set up that thing, and how does, like, how where's the guarantee that there's going to be a return for you, and who's calling the shots on whether you're going to get a return or not?
Yeah, that's a good question. I don't know exactly how. There is a sort of like organization that is,
I would think there'd have to be.
Yeah, that somehow is like that set up the protocol, and there is like some servers out there that are like in charge of sort of like moderating this. But again, it's sort of distributed and decentralized, and so like
for now,
yeah, that's true. But like whenever, it's kind of hard to explain without getting kind of too into the math. Whenever you find a solution to this sort of math problem to verify a block, it's very easy to check to see if that's a correct solution. And so like everybody on the network without any centralized body can tell that that's sort of the correct solution. And so it's the kind of thing where it's like, it's really not that difficult to be able to sort of come to a quick agreement that like you did the proof of work, and so you are the one that gets the reward for it because you've created this next block. And so it's like it's kind of a hard, it's designed to be very hard to like cheat, and that it's designed to not really need anybody to be sort of like adjudicating this sort of thing. Yes, somehow you do need your Bitcoin wallet to go up by a certain amount, and I'm not sure what the relationship is between finding that solution and your Bitcoin wallet going up. I don't know who pushes a button on a thing to make that go up somehow, or if it's a purely mathematical thing. I actually don't. Once you find that solution, do you get access to a code that you can redeem something? I actually don't know. But
you got time for one more question?
Yeah, let's do it.
All right. If it's too broad, we can pick it up next time.
Okay, cool. Yeah.
The history of the internet. I know it started in colleges, connecting college computers and so forth. And I think our government was using a form of the internet going back to the 70s and 60s.
Yeah, DARPA. Yeah.
Yeah. 95-ish started to go mainstream. I think 96 maybe with the public, so to speak. And that was always in the beginning, the Wild West, and it was freedom, and it was like, no government regulation and all that stuff. But I always wondered, like, well, who decides that you can have, greendot.com and someone else can't take it? Like, so the Internic, or what was the name of the company that was running the domains? Wasn't there a consortium or something that was in charge of the internet? Like, that's another example of something that was supposed to be organically grown, but there always felt like there was some hand of control over it.
Yeah.
So the whole domain thing was always puzzling to me. Like, who sets the domains? Who dictates and issues them out? And who creates new ones and just tells you that you have to accept them? And that kind of thing's puzzling to me.
Yeah. There are organizations, Yeah, and this is again something that I wish I knew more about, but
Okay.
I actually don't know the full details on.
Coop
it.
steak.
Coop steak, but there are like actual like it's like a non-profit governing body that is like in charge of like whenever we added a whole bunch of top level domains like .class,
Talk.
.ninja, .whatever,
Yeah.
Is that
Is
.space.
that the NEINTER?
It could be, yeah. I don't know. The domain name like the DNS server, domain name server.
Yeah.
That's what, whenever you go and you type in like www.google.com, that like your browser is taking like Google and it's asking this sort of like domain name system. Like,
Got it.
Who is Google? Like, is there an IP address associated with Google? And it starts with like the root domain name system, and then it sort of goes from there and it follows like a tree. And the root domain name system that has like addresses is distributed, like the Department of Defense has one server. I think like University of California has one because they were in the game from the very beginning. Europe has one. So there's like some root servers that's distributed though. They're all over the world. And then I think VeriSign, which is a private company, has like one of the root domain name servers. So if any one of those goes down, it's completely redundant. You could still like access it through another one. And then those guys kind of say like, okay, you actually want this IP address, which will take you to like Facebook's headquarters, and then they have their own sort of like server, right? And so, but who decides like who gets to be a root server? What are the protocols, right? What are the different domain names? Like, there's like actual organizations that like governments and like universities and people sit on that like kind of decide in some sort of democratic way.
I would hope.
Stuff. So yeah, no, I think it is still they are like NGO entities, like non-governmental entities that have a I believe, I guess I can't say because I haven't looked it up, but I believe it's somewhat transparent if you were to look up exactly like how they make these decisions.
So like the companies that GoDaddy and Register.com and some of the other ones are interfacing with to quote unquote license out the use of the domains.
Yeah, how did they get them in the first place is what you're asking. Yeah, I'm not 100% sure. At the end of the day, somebody has to sort of like get a whole block of IP addresses somehow, because there's only so many IP addresses.
Exactly.
Right. We recently increased the number of IP addresses by changing like the total bit length of the number associated with the address.
Okay.
Right? Just like how your address could be a 3-digit number if there aren't very many houses on your block, or a 4-digit number. We increased the number of digits of IP addresses to be IP version 4 or whatever, because the internet just got bigger, and so we needed more digits. But yeah, so like I'm not sure how that block of digits, how the block of IP addresses kind of gets allocated to a particular company so that they can then sell it, because it does seem like they shouldn't be allowed to just make money off of like a public resource like that. So they must somehow be contributing to like.
Hopefully, it's a consortium. I would think.
I think a lot of these very upper level planning things are sort of consortiums that everyone who's sort of maintaining the internet, like IP, so like the service providers like Verizon and AT&T, plus people like the U.S. military and stuff like that, and also like nation states and stuff that all have a big stake in it. Like I think they all sort of like have people that are sitting on this.
It's insane.
But it is crazy. But one cool thing about the internet is, like I was saying about the root servers, it's kind of like there are sort of like redundant copies of all this information sort of everywhere. Like Google has like copies of the internet like in different places.
Yeah, like, well, thank goodness.
So it is kind of interesting how it is. A lot of the decisions about standards are centralized, but the internet itself is still kind of decentralized, right? Like when you go to a website, that website is held in an office building somewhere, right? It's not held like in the White House. Like,
right.
How to communicate with it might be determined by some governing body that maybe the White House sits on, but like at the end of the day, like that information and that content, it's you and this person that's really determining that interaction, which is like kind of cool.
My friend, I can't thank you enough.
It's been good.
This is awesome.
Always
man.
happy. We were all over the place today, but that was fun.
But you hit everything I wanted to talk about. I appreciate it.
Yeah, it's cool. Yeah,
We'll do it again soon.
absolutely.
All
You
right.
know how to find me.
Thanks
again. See you, everybody.
We'll see you, friends.
Hello, you're listening to the Eric McKenna Project.